Introduction. Hey kids, today we will learn quantum mechanical model of atom. Matter has dual behavior wave as well as particle. Heisenberg's uncertainty principle is only applicable to small particle such as electron. The region of the atom where probability of finding electron is maximum is called orbital. Orbitals are characterized by a set of numbers known as quantum numbers. The energy, size, shape and orientation of the electron orbital can be specified by the use of three quantum numbers. There are principal quantum number, azimuthal quantum number and magnetic quantum number. So, throughout this model, we will quantum mechanical model of atom. Objectives. At the end of this lesson, you will be able to discuss dual behavior of matter, state Heisenberg's uncertainty principle, describe quantum mechanical model of atom. Towards quantum mechanical model of the atom, dual behavior of matter. In 1923, Louis de Broglie, the French physicist, proposed that like light, matter also has dual character. It exhibits wave as well as particle nature. He derived a relationship for the calculation of wavelength lambda and of the wave associated with the particle of mass m moving with velocity v as given by lambda is equal to h by mv or lambda is equal to h by p, where h is Planck's constant and p is momentum of the particle. The waves associated with material particles or objects in motion are called matter waves or de Broglie waves. According to the de Broglie concept, the electrons are not only particles but also have wave character associated with them. Therefore, for the wave to be completely in phase, the circumference of the orbit should be integral multiple of wavelength lambda. But from the de Broglie equation we know that lambda is equal to h upon mv. Hence, 2 pi r is equal to n into h by mv, where mvr is equal to n into h by 2 pi. Heisenberg's uncertainty principle. Heisenberg's uncertainty principle states that it is not possible to determine simultaneously the position and momentum of a small moving particle, such as electron, with entire certainty. Mathematically, it may be expressed delta x into delta p greater than or equal to h by 4 pi, where delta x is equal to uncertainty in position, delta p is equal to uncertainty in momentum is equal to m delta v. Delta v is uncertainty in velocity of particle, m is the mass of the particle, h is equal to Planck's constant. So, it can be concluded that one can define the position of small particles. The less certainty one is able to define its velocity or momentum and vice versa. Significance of uncertainty principle. The effect of Heisenberg uncertainty principle is significant only for motion of microscopic objects and is negligible for macroscopic objects. In case of microscopic objects such as electrons, the interaction of the striking photon of light with the particle will cause appreciable displacement of the particle from its normal path. As a result of this, the particle undergoes a considerable change in its path and velocity or momentum due to the impact of a single photon used to observe it. Thus, the very act of measuring the position of the microscopic particle causes a change in its momentum. The collision of photon with the electron sends it in an unpredictable direction. In our daily life, this principle has no significance. This is because we come across only large objects, that is, the objects which we can observe with naked eye, without altering their motion. The position and velocity of these objects can be determined accurately because in these cases, during the interaction between the object and the measuring device, the change in the position and velocity are negligible. Example: calculate the uncertainty in position of a dust particle with mass equal to 1 mg if the uncertainty in its velocity is 5.5 into 10 raised to the power minus 20 meter per second. Solution given delta V is equal to 5.5 into 10 raised to the power minus 20 meter per second. M is equal to 1 milligram is equal to 1 into 10 raised to the power minus 3 gram. H is equal to 6.626 into 10 raised to the power minus 34 joule second. From the formula, delta X into M delta V greater than or equal to H upon 4 pi. Uncertainty in position can be found as delta X greater than or equal to H upon 4 pi M delta V. Substitute the value of H delta V M, we get delta X greater than or equal to 6.626 into 10 raised to the power minus 34 divided by 4 into 3.14 into 10 raised to the power minus 3 into 5.5 into 10 raised to the power minus 20. Delta X greater than or equal to 9.59 into 10 raised to the power minus 13 meter. Reasons for the failure of the Bohr model. The wave character of the electron is not considered in Bohr model, and the orbit can be defined only if both the exact position and the exact velocity of the electron at the same time are known. This is not possible according to the Heisenberg uncertainty principle. Bohr model of the hydrogen atom ignores dual behavior of matter and also contradicts Heisenberg uncertainty principle. Quantum mechanical model of atom. Quantum mechanics is a theoretical science that takes into account the dual nature of matter, hydrogen atom and Schrödinger equation. Based on quantum mechanics, a new model of atom was developed, and this model is known as quantum mechanical model. In this model, behavior of the electron in an atom is described by an equation known as the Schrödinger wave equation, where x, y, and z are the three space coordinates. M is mass of the electron, h is the Planck's constant, E is the total energy, and V is the potential energy of the electron. Xi is amplitude of the electron wave and is called wave function. Sometimes the Schrödinger wave equation is written in the form h xi is equal to E xi, where h is a mathematical operator known as Hamiltonian operator. Significance of Xi. As a moving electron is associated with a wave, and a wave is completely defined by its amplitude. Therefore, Xi refers to the amplitude of the electron wave. It has got no physical significance. However, the square of Xi, that is Xi square, has a physical significance. In electron wave, Xi square gives the intensity of the electron at any point. In other words, the knowledge of Xi square is helpful in assessing the probability of electron in a particular region. Thus, Xi square is called probability density and Xi is referred to as probability amplitude. The solution of the Schrödinger equation for the hydrogen atom gives the energy levels that electron can occupy and the wave function of the electron associated with each energy level. Orbitals and quantum numbers. An orbital may be defined as that region of space around the nucleus where the probability of finding an electron is maximum. Orbitals are designated by a set of numbers known as quantum numbers. In order to specify energy, size, shape, and orientation of the electron orbital, three quantum numbers are required. These are principal quantum numbers, azimuthal quantum number, and magnetic quantum number. The principal quantum number, n. Principal quantum number tells us in which principal energy level the electron is present. It can have any whole number values such as 1, 2, 3, 4, etc. The energy levels or energy shells corresponding to these numbers are designated as K, L, M, N, etc. Energy of the electron in a hydrogen atom is related to principal quantum number by the following relation. En is equal to minus k square into 2 into pi square into m into e raised to the power 4 divided by n square into h square is equal to minus 2.18 into 10 raised to the power minus 18 divided by n square joule, where m is equal to mass of electron, e is equal to Charge on electron. H is equal to Planck's constant. En is equal to energy of the electron in nth principal shell. N is equal to principal quantum number used to designate the principal shell. K is equal to Coulomb's law constant. Azimuthal quantum number. L. Azimuthal quantum number determines angular momentum of the electron. This is denoted by L. The value of L gives the sublevel or subshell in which the electron is located. It also determines the shape of the orbital in which the electron is located. The number of subshells within a principal shell is determined by the value of n for that principal energy level. Thus, L may have all possible whole number values from 0 to n-1 for each principal energy level. For n is equal to 1, L can have only one value, that is 0. It means that an electron in first energy level can be present only in S subshell. L is equal to 0. So first energy level has only one subshell, that is 1s. For n is equal to 2, L can have values 0 and 1. It means that the electron in second principal energy level may be located either in S subshell L equal to 0 or P subshell L is equal to 1. So second energy level has only two subshells, that is 2s and 2p. For n is equal to 3, possible values of L are 0, 1 and 2. This implies that an electron in third principal energy level may be present either in S subshell L is equal to 0 or P subshell L is equal to 1 or D subshell L is equal to 2. So, third energy level has three subshells, that is 3s, 3p and 3d. Similarly, fourth energy level n is equal to 4 can have four subshells, 4s, 4p, 4d and 4s. Magnetic orbital quantum number, ML.
Magnetic orbital quantum number refers to the different orientations of electron cloud in a particular subshell. These different orientations are called orbitals. The number of orbitals in a particular subshell within a principal energy level is given by the number of values allowed to ML, which in turn depends on the values of L. The possible value of ML range from plus L through 0 to minus L, thus making the total of 2L plus 1 values. Thus, in a subshell, the number of orbitals is equal to 2L plus 1. For L is equal to 0, ML can have only one value. ML is equal to 0. It means that S subshell has only one orbital. For L is equal to 1, ML can have three values, plus 1, 0 and minus 1. This implies that P subshell has three orbitals. For L equal to 3, ML can have 7 values, plus 3, plus 2, plus 1, 0, minus 1, minus 2, minus 3. It means that F subshell has 7 orbitals.
Spin quantum number ms. Spin quantum number determines the orientation of spin angular momentum. Spin angular momentum is quantized and can have two orientations relative to a chosen axis. This spin quantum number can have only two values, which are plus half and minus half. The plus half value indicates clockwise spin represented by an arrow pointing upwards, and the other indicates anti-clockwise spin represented by an arrow pointing down. Shapes of atomic orbitals. An orbital wave function psi can be written as a product of two functions, the radial function and the angular function. So, the complete wave function represents an orbital in which the radial part psi r depends upon quantum number n and l, and it tells us about the size of the orbital, whereas the angular part depends upon quantum number l and ml and tells us about the shape of the orbital. The positive and negative signs indicate that the orbital wave function is positive or negative in a particular region. It has been observed that s orbitals are independent of angular wave function. All s orbitals are spherically symmetrical. P and d orbitals depend upon radial as well as angular wave function. Shapes of atomic orbitals. Probability density. A graph of xi square as a function of distance from the nucleus is called probability density curve. The regions of space around the nucleus where the probability of finding the electron is maximum are called orbital. Boundary surface diagrams. A boundary surface, also known as contour surface, is drawn in space for an orbital on which the value of probability density xi square is constant. A boundary surface which encloses the regions of maximum probability, say 90%, best describes the shape of the orbital. The boundary surface diagrams for s orbitals are spherical in shape. The size of the s orbital, however, increases with increase in value of n. The boundary surface diagrams of 3 2p orbitals are not spherical. Each p orbital consists of 2 lobes which are separated by a region of zero probability called node. The 3 2p orbitals lie along x, y and z axes respectively and are designated as 2px, 2py and 2pz. Charge cloud picture of orbitals. For s orbitals, the probability of finding the electron is same in all directions at a particular distance. In other words, s orbitals are spherically symmetrical. The s orbitals of higher energy levels are also spherically symmetrical, however, they are more diffused and have spherical shells within them where probability of finding the electron is zero. These are called spherical nodes. In 2s orbitals, there is one spherical node. Energies of orbitals. A diagram representing relative energies of various orbitals in an atom is called energy level diagram. In hydrogen atom, there is only one electron which is present in orbital in ground state. However, in excited state, the electron may jump to any of the orbitals belonging to higher energy levels. All the orbitals of a particular energy level have same energy in hydrogen and hydrogen-like atoms. For example, 2s and 2p orbitals have same energy. The orbitals having the same energy are called degenerate orbitals. Energy level diagram of multi-electron atoms. In case of multi-electron atoms, the energies of various orbitals depend not only upon the nuclear charge but also upon the other electrons present in the atom. Main characteristics of this diagram are: number 1, the different subshells of a particular energy level may have different energies. For example, energy of 2s subshell is different from the energy of 2p subshell. Number 2, in a particular energy level, the subshell having higher value of L has higher energy. Increasing order of energies of different types of subshells in a particular energy level is: number 3, as the value of N increases, some subshells of lower energy level may have energy higher than the energy of some subshells of higher energy level. Number 4, the increasing order of energies of various subshells is: the relative order of energies of various subshells in a multi-electron atom can be predicted with the help of N plus L rule. According to this rule, number 1, in neutral atoms, a subshell with lower value N plus L has lower energy. Number 2, if two subshells have equal value of N plus L, the subshell with lower value of N has lower energy. Filling of orbitals in atoms. Aufbau rule. According to this rule, the electrons are added progressively to the various orbitals in their order of increasing energies, starting with the orbital of lowest energy. Increasing order of energies of various orbitals are: Pauli's exclusion principle. This principle states that no two electrons in an atom can have same set of all the 4 quantum numbers. From this, it follows that an orbital cannot have more than 2 electrons. Moreover, if an orbital has 2 electrons, then they must have opposite spins. Hund's rule of maximum multiplicity. This rule states that the pairing of electron in the orbital of particular subshells P, D or F does not take place until all the orbitals of the subshell are singly occupied. Moreover, the singly occupied orbitals must have the electrons with parallel spin. Electronic configuration of atoms. In order to represent electron population of an orbital, the principal quantum number n is written before the orbital symbol, while the number of electrons in the orbital is written superscript near the right-hand top of the orbital symbol. If we have 2 electrons in the s orbital of first energy level, then it is written as 1s squared. For hydrogen, for helium, for lithium, for beryllium, for boron, for carbon, for nitrogen, for oxygen. Stability of completely filled and half-filled subshells. The completely filled and completely half-filled subshells are stable due to symmetrical arrangement. The electronic configuration in which all the orbitals of same subshell are either completely filled or exactly half-filled have relatively more symmetrical distribution of electrons and therefore lend more stability to the system. Stability due to exchange energy. The half-filled or fully filled degenerate orbitals have more number of exchanges and consequently have large exchange energy of stabilization. The exchange means shifting of electrons from one orbital to another within same subshell. Let us compare the number of exchanges in 3d4, 4s2 and 3d5, 4s1 configuration of chromium. Thus, in 3d4 arrangement, electron exchanges are 6, which implies that there are 6 possible arrangements with parallel spin in 3d4 configuration. The total number of electron exchanges in 3d5 arrangement is larger, which lends it to greater stability. Did you know? Atom scale imaging unlocks exact structure of glass. Intel plans to release its first 22 nanometer quad-core atom system on a chip at the start of 2014. Summary. Let us summarize what we have learned. Matter exhibits wave as well as particle nature. Wavelength of the wave associated with a particle of a mass m moving with velocity v as given below, where h is Planck's constant and p is momentum of the particle. Heisenberg's uncertainty principle states that it is not possible to determine simultaneously the position and momentum of a small moving particle, such as electron, with entire certainty. Mathematically, it may be expressed as Schrödinger wave equation, where x, y and z are 3 space coordinates. M is mass of electron, h is Planck's constant, E is the total energy and V is the potential energy of the electron. Xi is amplitude of the electron wave and is called wave function. Principal quantum number tells us in which principal energy level the electron is present. It is denoted by n. Azimuthal quantum number determines angular momentum of the electron. This is denoted by L.
Magnetic orbital quantum number refers to the different orientations of electron cloud in a particular subshell.
This is denoted by ML. According to the Aufbau rule, the electrons are added progressively to the various orbitals in their order of increasing energies, starting with the orbital of lowest energy. Pauli's exclusion principle states that no 2 electrons in an atom can have same set of all the 4 quantum numbers. From this, it follows that an orbital cannot have more than 2 electrons. The completely filled and completely half-filled subshells are stable due to symmetrical arrangement and stability due to exchange energy. Introduction. Hello Rohit, how are you?
Good morning, Dad. I am good.
What are you doing?
I am doing chemistry, Dad.
Whoa, chemistry is a good subject to study.
Thanks, Dad.
Do you know that everything is made up of atoms?
How is it possible, Dad? And what is atom?
Atoms are the basic building blocks of ordinary matter. as you know that everything is made up of molecules and atoms joined together to form a molecule.
Okay, Dad. What kind of materials are there in the atoms?
Atoms consists of electrons, protons and neutrons and central core which is called nucleus.
It sounds interesting. Can you tell me more of it?
Yes, Rohit. In this lesson, you will study the structure of atom. Objectives. At the end of this lesson, you will be able to explain subatomic particles, discuss atomic models, define atomic number and mass number, define isobars and isotopes, explain developments leading to the Bohr's model of atom, explain Bohr model of hydrogen. Subatomic particles. Discovery of electron. A discharge tube is long glass tube. This tube is fitted with metal electrodes on either end, across which high voltage can be applied. The tube is also connected to a vacuum pump for controlling the pressure of gas inside the discharge tube. There is a coating of phosphorescent material behind the anode. When the gas pressure inside the discharge tube is 1 atmosphere, no electric current flows through the tube. If the gas pressure is reduced to about 10 to the power minus 2 atmospheres and a potential difference of about 10,000 volts is applied to the electrodes, an electric current flows and at the same time light is emitted by the gas. If the gas pressure is reduced to 10 to the power minus 4 atmospheres, the emission of light ceases. Instead, the tube glows, fluorescence with a faint greenish light. This fluorescence was caused due to the bombardment of the walls of the tube by rays emanating from cathode. These rays were called cathode rays. These rays were found to consist of negatively charged material particles called electrons. Properties of cathode rays. Cathode rays travel in straight lines. An object placed in the path of cathode rays casts a sharp shadow. It shows that cathode rays travel in straight line. Effect of electric field. When electric field is applied to a stream of cathode rays, they are deflected towards positive plate. It showed that cathode rays themselves are negatively charged. Effect of magnetic field. When magnetic field is applied perpendicular to the path of the cathode rays, they get deflected in the direction expected for negative particles. This further confirmed that cathode rays are negatively charged. Charge to mass ratio of electron. On simultaneous application of electric and magnetic fields applied perpendicular to each other, it is possible to adjust the two fields so that the cathode rays strike the fluorescent screen at the same position as they do when neither field is applied. The value of charge to mass ratio of the electrons was found to be 1.76 into 10 raised to the power 8 coulombs per gram. The E by M ratio for the particles in the cathode rays was found to be same irrespective of the nature of cathode or the nature of the gas taken in the discharge tube, thus showing that the electrons are universal constituent of all matter. Charge on the electron. R. A. Millikan found the value of charge on electron by oil drop experiment. The oil droplet enters the apparatus through a small hole and are allowed to fall in between two charged plates. The motion of the droplets is observed with a microscope. The space between charged plates is irradiated with X-rays. The X-rays ionize the molecules of air. One or more electrons thus produced may be absorbed by an oil droplet. Thus, the charge on an electron E is equal to 1.6 into 10 raised to the power minus 19 coulomb. Mass of the electron Me is equal to 9.31 into 10 raised to the power minus 31 kilogram. Discovery of protons and neutrons. Goldstein in 1886 used a perforated cathode in a discharge tube. On passing the electric discharge at low pressure, he observed a new type of rays carrying a positive charge streaming behind the cathode. These rays were named as anode rays or canal rays. Properties of anode rays. The charge to mass ratio of the particles in the anode rays was found to depend upon the nature of the gas in the discharge tube. It was observed that E by M ratio was maximum when hydrogen gas was taken in the discharge tube. This indicated that the positive ions formed from hydrogen are lightest. These lightest positively charged particles were named protons. The neutrons was discovered by Chadwick. He made alpha particles to strike on beryllium, and neutral particles are emitted, and these were called neutrons. Atomic models. Thomson model of atom. He proposed that an atom consists of a uniform sphere of positive electricity in which the electrons are distributed more or less uniformly. This model of atom is known as the plum pudding model or raisin pudding model. Rutherford's nuclear model of atom. Rutherford's nuclear model of atom. Alpha particle scattering experiment. The experiment involved the bombardment of a thin sheet of gold by alpha particles. These particles were obtained in the form of a narrow beam by passing through a slit in a lead plate. A circular screen coated with zinc sulfide ZnS was placed around the foil to detect the deflection suffered by alpha particles. Whenever an alpha particle struck the screen, a tiny flash of light was produced at that point. Observations. Number 1. Most of the alpha particles, nearly 99%, passed through a gold foil undeflected. Number 2. Some of the alpha particles were deflected by small angles. Number 3. A few particles were either deflected by very large angles or were actually reflected back along their path. Explanation of Rutherford's nuclear model of atom. He explained his observations as follows. Number 1. Since most of the alpha particles pass through the foil undeflected, it indicates that the most of the space in an atom is empty. Number 2. Alpha particles, being positively charged and having considerable mass, could be deflected only by some heavy positively charged center. The small angle of deflection of alpha particles indicated the presence of a heavy positive center in the atom. Rutherford named this positive center as nucleus. Number 3. Alpha particles which make head-on collision with heavy positive center are deflected through large angles. Since the number of such alpha particles is very small, the space occupied by the heavy positive center must be very small. Main points of Rutherford's nuclear model of atom. Main points of this model are: Number 1. Most of the mass and all the positive charge of an atom are concentrated in a very small region called nucleus. Number 2. The nucleus is surrounded by electrons which are revolving around it at very high speeds. The electrostatic force of attraction between electrons and the nucleus is balanced by the centrifugal force acting on the revolving electrons. Number 3. Total negative charge on the electrons is equal to the total positive charge on the nucleus, so that atom on the whole is electrically neutral. Number 4. Most of the space inside an atom is empty. Atomic number and mass number. The number of unit positive charges on the nucleus of an atom of the element is called atomic number of the element. Atomic number of an element is equal to the number of protons in the nucleus of its atom or the number of extranuclear electrons. Generally, it is denoted by the letter Z. Atomic number Z is equal to number of protons is equal to number of electrons. Mass number. Total number of protons and neutrons in the nucleus is called mass number of the atom. It is generally represented by the letter A. Mass number A is equal to number of protons plus number of neutrons is equal to number of nucleons. Isobars and isotopes. Mass number and atomic number of an element are indicated as: isotopes of an element are the atoms of the element with same atomic number but different mass numbers. The 3 isotopes of hydrogen can be represented. The atoms of different elements which have same mass number are called isobar. For example, drawbacks of Rutherford model. Number 1. According to electromagnetic theory, a charged particle when accelerated emits energy in the form of electromagnetic radiation. According to Rutherford's model, electrons are revolving around the nucleus. This means electrons would be in state of acceleration all the time. Since electrons are charged particles, so electrons should emit radiation, and as a result, they get slowed down and finally fall into the nucleus by following a spiral path. Rutherford's model failed to explain stability of atoms. Number 2. It does not explain the distribution of electrons around the nucleus and does not tell us anything about their energies. Number 3. Rutherford's model also failed to explain the existence of certain definite lines in the hydrogen spectrum. Development leading to Bohr's model of atom. Wave nature of electromagnetic radiation. According to the Maxwell's wave theory of light, light is transmitted in the form of electromagnetic waves. These waves are associated with oscillating electric field and magnetic field. These two fields are perpendicular to each other and also to the direction of propagation. Parameter of the wave. Wavelength. It may be defined as the distance between two neighboring crests or troughs of the wave. It is represented by lambda and is generally measured in angstrom units or nanometers. 1 angstrom is equal to 10 raised to the power minus 10 meter. 1 nanometer is equal to 10 raised to the power minus 9 meter. Frequency. It may be defined as the number of waves which pass through a particular point in 1 second. It is represented by mu. Its units are cycles per second or hertz. Velocity. The distance traveled by a wave in 1 second is called velocity of the wave. It is denoted by letter c. The frequency and wavelength are related to the velocity c by the relation c is equal to mu into lambda. Its unit is meter per second. Wave number. It may be defined as the number of wavelengths per unit length. It is equal to the inverse of wavelength. It is denoted by mu bar. Its unit is the reciprocal of wavelength unit. It is generally expressed as 1 by centimeter or 1 by meter. Mu bar is equal to 1 by lambda. Amplitude. It is the height of a crest or depth of a trough of a wave. It is generally expressed by the letter A. The amplitude of a wave determines the intensity of radiation. Particles nature of electromagnetic radiation. Planck's quantum theory. Wave theory of radiation cannot explain the phenomena of photoelectric effect and black body radiation. Black body radiation. An ideal black body is a perfect absorber and perfect emitter of radiation. When such a body is heated, it becomes red hot. In other words, it emits red-colored light. As the temperature is further increased, the color of the radiation emitted changes from red to yellow to white and finally to purple as the temperature becomes very high. This implies that wavelength of radiation emitted by a black body decreases with increase in temperature. Consider the graph from right to left. At a given temperature, intensity of radiation emitted increases with decrease of wavelength, reaches a maximum value at a given wavelength, and then starts decreasing with further decrease of wavelength. Particle nature of electromagnetic radiation. Planck's quantum theory. Planck's quantum theory of radiation. Radiant energy is emitted or absorbed not continuously but discontinuously in the form of small packets of energy called quanta. The amount of energy associated with a quantum of radiation is proportional to the frequency of radiation, where h is a constant known as Planck's constant and is equal to 6.625 into 10 raised to the power minus 34 joule second. A body can emit or absorb energy only in terms of the integral multiples of quantum, that is, E is equal to nh nu, where n is equal to 1, 2, 3, 4, etc. Photoelectric effect. Photoelectric effect may be defined as the phenomenon of ejection of electrons from the surface of a metal when light of suitable frequency strikes it. The electrons thus ejected are called photoelectrons. When light of particular frequency strikes the metal surface, electrons are ejected from the metal surfaces, which are detected by the detector. For a particular metal, there exists a threshold frequency V0, such that at frequencies below the threshold, no electrons are emitted, no matter how large the intensity is or how long the radiation occurs. The number of photoelectrons emitted per second is directly proportional to the intensity of the incident radiation but does not depend upon its frequency. According to Einstein, electrons in metals are held by some attractive forces. To overcome these forces, certain minimum amount of energy is required, which is characteristic of the metal. This is called photoelectric work function W0. W0 is equal to h nu naught. Einstein equation can be written as h nu is equal to h nu naught plus Ke. Ke is equal to h nu minus h nu naught. Dual behavior of electromagnetic radiation. The photoelectric effect could be explained considering that radiations consist of small packets of energy called quanta. These packets of energy can be treated as particles. On the other hand, radiations exhibit phenomena of interference and diffraction, which indicates that they possess wave nature. So it may be concluded that radiations possess dual nature, that is, particle nature as well as wave nature. Evidence for the quantized electric energy levels. Atomic spectra. The phenomenon of splitting of a beam of light into radiation of different frequencies after passing through the prism is called dispersion, and the pattern of radiations obtained after dispersion of beam is called spectrum. In case of dispersion of sunlight, the 7 colors obtained change from violet to red without any discontinuity, which means each color bends into the other. Such a spectrum is called continuous spectrum. Emission and absorption spectra. When an element is excited by some method, such as by heating, by passing electric current, or by passing electric discharge, the atoms of the element emit electromagnetic radiations of definite frequencies. The arrangement of these radiations in the order of increasing wavelength or decreasing frequencies is called emission spectrum of the element or atomic spectrum. Atomic spectrum of an element can be used to identify the element and is sometimes called fingerprint of its atoms. Atomic spectra of most of the elements consists of number of bright lines separated by dark bands. That is why atomic spectrum is also known as line spectrum. Absorption spectrum is the spectrum formed by the electromagnetic radiation that has passed through a medium in which radiation of certain frequencies is absorbed. Line spectrum of hydrogen. When an electric discharge is passed through hydrogen gas, its molecules dissociate into hydrogen atoms. The excited hydrogen atoms thus produced emit electromagnetic radiations of discrete frequencies. The spectrum obtained consists of a large number of sharp lines. Each line corresponds to a particular frequency of light emitted by hydrogen atoms. The lines in the emission spectrum of hydrogen are classified into 5 series as follows. Lyman series, it is in ultraviolet region. Balmer series, it is in visible region. Paschen series, Brackett series and Pfund series, these are in infrared region. The spectral lines are expressed in terms of wave numbers. Then the lines in the visible region obey the formula. Wave number is equal to 1,09,677 into 1 by 2 square minus 1 by n square per centimeter, where n is an integer equal to or greater than 3, that is, n is equal to 3, 4, 5 and so on. After this, Rydberg gave a more general formula, which is applicable to all the series in the hydrogen spectrum. Wave number is equal to 109677 into 1 by n1 square minus 1 by n2 square per centimeter, where n1 and n2 are integers, such that n2 is greater than n1. For a particular series, n1 is constant. The value 109677 per centimeter is called Rydberg constant for hydrogen. Bohr's model for hydrogen atom. Bohr's model of atom is based upon quantum theory of radiations. Main points of this model are: the electrons in an atom revolve around the nucleus only in certain selected circular orbits. These orbits are associated with definite energies and are called energy shells or energy levels. These are numbered as 1, 2, 3, 4, etc. or designated as K, L, M, N, etc. shells. Only those orbits are permitted in which the angular momentum of the electron is a whole number, multiple of h by 2 pi, where h is Planck's constant, that is, angular momentum of the electron. MVR is equal to nh by 2 pi, where n is equal to 1, 2, 3, etc., where m is the mass of the electron, v is the velocity of the electron, and r is the radius of the orbit. In the other words, angular momentum of electron in an atom is quantized. As long as the electron remains in a particular orbit, it does not lose or gain energy. This means that energy of an electron in a particular orbit remains constant. That is why these orbits are called stationary states. When energy from some external source is supplied to the electron, it may jump to some higher energy level by absorbing a definite amount of energy equal to the difference in the energy between the two energy levels. When the electron jumps back to the lower energy level, it radiates same amount of energy in the form of the photon of radiation. Delta E is equal to E2 minus E1 is equal to h nu. Nu is equal to E2 minus E1 by h, where nu is the frequency of the emitted radiation. Bohr's model for hydrogen atom. Quantization of energy and Bohr's model. According to the Bohr's model, energy of the electron in an atom is quantized. Quantization means that a quantity cannot vary continuously to have any arbitrary values, but can change only discontinuously to have some specific values. To illustrate this point, let us consider a simple example. Suppose a person moves down a staircase, then energy of the person changes discontinuously and he can have only certain definite values of energy corresponding to the energies of various steps. Energy of the person in this case is quantized. On the other hand, if the person moves down a ramp, then his energy changes continuously and he can have any value of energy corresponding to any point on the ramp. Energy in this case is not quantized. So, according to Bohr's model, energy of an electron in an atom is quantized. The main successes of Bohr's model are: Number 1. Bohr's model could explain the stability of an atom. Number 2. Bohr's theory helped in calculating energy of an electron in a particular orbit of hydrogen. The expression is En is equal to minus k square into 2 into pi square into m into e raised to the power 4 divided by n square into h square, where m is mass of the electron, e is charge on the electron, h is Planck's constant, k is Coulomb's law constant. On substituting the value of constants, we get En is equal to minus 1312 by n square kilojoule per mole. Bohr gives an expression for the radius of an orbit in hydrogen atom. Rn is equal to n square into h square divided by 4 into pi square into k into m into e square. Rn is equal to n square into 0.529 into 10 raised to minus 10 meter. Rn is equal to n square into 0.529 angstrom. Thus, as n increases, the radius of the orbit increases. The radius of first orbit of hydrogen is equal to 0.529 angstrom. This is also known as Bohr's radius. Explanation of line spectrum of hydrogen. In hydrogen atom, there is one electron which is present in first orbit in ground state. When energy is supplied, such as by passing electric discharge, this electron may be excited to some higher energy level. Since in a sample of hydrogen there are large number of atoms, the electrons in different atoms absorb different amounts of energies and are excited to different high energy levels. For example, let us consider the electron present in the fourth energy level n is equal to 4 of different hydrogen atoms. In some atoms, it may come to ground state n is equal to 1 by direct jump, while in some others, it may first jump to second energy level n is equal to 2 and then to first energy level n is equal to 1, while in still others, it may come to ground state via third n is equal to 3 and second energy levels n is equal to 2. The lines which arise due to the transitions from high energy levels to first energy level are grouped as Lyman series. Similarly, the lines obtained as a result of transitions of electrons from high energy levels to second, third, fourth and fifth energy levels give rise to Balmer-Paschen bracket and Pfund series respectively. Suppose an electron from a higher orbit having n is equal to n2 jumps to a lower energy level having n is equal to n1 in hydrogen atom. As a result of this transition, the electron emits energy in the form of a photon radiation. Then the frequency of the emitted photon is frequency is equal to 3.29 into 10 raised to the power 15 into 1 by n1 square minus 1 by n2 square per second. In terms of wave number, 109677 into 1 by n1 square minus 1 by n2 square per centimeter. Limitations of Bohr's model. Number 1. Bohr's model could not explain the spectra of atoms containing more than one electron. Number 2. In the presence of a magnetic field, each spectral lines get split up into closely spaced lines. This phenomenon, known as Zeeman effect, could not be explained by Bohr's model. Similarly, the splitting of spectral line under the effect of applied electric field, that is Stark effect, could not be explained by Bohr's model. Reasons for the failure of Bohr model. The wave character of the electron is not considered in Bohr model. An orbit can be defined only if both the exact position and the exact velocity of the electron at the same time are known. This is not possible according to the Heisenberg uncertainty principle. Bohr model of the hydrogen atom ignores dual behavior of matter and also contradicts Heisenberg uncertainty principle. Did you know? Atom smashing scientists reach highest ever recorded man-made temperature, 1 lakh times hotter than the sun's interior. Scientists there collided lead ions to create a searingly hot subatomic soup known as quark-glued plasma at about 5.5 trillion Celsius, the hottest temperature ever recorded in an experiment. Summary. Let us summarize what we have learnt. Electrons are negatively charged. Charge to mass ratio of electron is 1.76 into 10 raised to the power 8 coulombs per gram. Rutherford shows that most of the mass and all the positive charges of an atom is concentrated in a very small region called nucleus. Mass number A is equal to number of protons plus number of neutrons is equal to number of nucleons. According to Maxwell's wave theory of light, electric and magnetic fields are perpendicular to each other and also to the direction of propagation. An ideal black body is a perfect absorber and perfect emitter of radiation. The amount of energy associated with the quantum of radiation is proportional to the frequency of radiation, where h is a constant known as Planck's constant and is equal to 6.625 into 10 raised to the power minus 34 joule second. Photoelectric effect may be defined as the phenomenon of ejection of electrons from the surface of a metal when light of suitable frequency strikes it. The electrons thus ejected are called photoelectrons. Atomic spectrum of an element can be used to identify the element and is sometimes called fingerprint of its atom. The lines in the emission spectrum of hydrogen are classified into 5 series as follows: Lyman series, Balmer series, Paschen series, bracket series and Pfund series. Rydberg gave a general formula which is applicable to all the series in the hydrogen spectrum. The value 109677 per centimeter is called Rydberg constant for hydrogen. Bohr gives an expression for the radius of an orbit in hydrogen atom. Rn is equal to n square into 0.529 angstrom. Introduction.
Come on, Dad. Let's get on the balloon.
Easy, Rohit, easy.
Yippee! It is going up now. We are flying like a bird. Dad, I want to ask you something.
Yes, Rohit, tell me.
How it gets into the air?
In this, we use gaseous fuel to heat up the air in the envelope to move the balloon off the ground and into the air.
Okay, Dad.
One more thing I want to share with you, that the gaseous state has no definite shape. In this lesson, you will learn gaseous and liquid states of matter. Objectives. At the end of this lesson, you will be able to explain intermolecular forces, distinguish between solid, liquid and gaseous state, state the gas laws, state ideal gas equation, state Dalton's law of partial pressures, describe kinetic molecular theory of gas, distinguish between ideal gases and real gases, discuss vapor pressure of liquids, define surface tension and viscosity. Intermolecular forces. The forces of attraction between molecules which keep molecules together are called intermolecular forces. The energy due to force of attraction between molecules is called molecular interactional energy. Molecular interactions lead to intermolecular attractive and repulsive forces. Attractive intermolecular forces are also called van der Waals forces, dispersion forces or London forces. Electrons are symmetrically distributed around the atom most of the time, but at any instant there may be some asymmetry in the distribution of electrons around the nucleus, resulting into an electric dipole. This dipole produces an electric field which distorts the electron distribution of neighboring atom or molecule, which also becomes dipole. These two dipoles will attract, and these forces of attraction between them are called dispersion or London forces. It occurs in non-polar molecules and even noble gases. For example, one atom has symmetrical distribution and the other has unsymmetrical distribution, and the atom with unsymmetrical distribution distorts the electron distribution of the other atom, results in a force of attraction. Dipole-dipole forces. These are the interparticle forces among the polar molecules. These forces arise due to electrostatic interactions between the oppositely charged ends of permanent dipoles. The positive end on one molecule attracts the negative end of the other molecule and vice versa. These charges are shown by delta. Dipole-induced dipole forces. It is the force of attraction between molecule having permanent dipole moment and other molecules having zero dipole moment, like CH4, CCl4, BF3, SO3, etc. For example, a polar molecule such as HCl can induce a dipole in an argon atom by distorting the electron cloud. An electrostatic attraction exists between the ion or permanent dipole and the induced dipole. The intermolecular force is called a dipole-induced dipole attraction. Hydrogen bond. Hydrogen bond is defined as the electrostatic force of attraction which exists between the covalently bonded hydrogen atom of one molecule and the electronegative atom of the other molecule. The hydrogen bond is represented by dotted line. For example, in case of hydrogen fluoride, the hydrogen bond exists between H atom of one molecule and fluorine atom of another molecule. Hydrogen atom should be bonded to a highly electronegative atoms such as fluoride, oxygen or nitrogen. Larger the electronegativity of the other atom, greater is the strength of hydrogen bond. Thermal energy. The energy which moves the molecules apart is called thermal energy. It is defined as the energy possessed by matter by virtue of its temperature and is also measure of thermal motion or movement of molecules. Intermolecular forces versus thermal interactions. The three states of matter are, in fact, the result of competition between the molecular interaction energy and thermal energy. In solids, the molecular interactions are very strong and the molecules possess low thermal energy. In liquids, a fine balance exists between attractive forces and thermal energy. Increase in temperature further increases the thermal energy, and ultimately a stage reaches when the molecules fall apart and behave almost as independent entities. This stage refers to gaseous state. Gaseous state. The state of matter in which the molecular forces of attraction between the particles of matter are minimum is known as gaseous state. Gases completely fill the container that holds them. Characteristics of gases. Gases or their mixtures are homogeneous in composition. Gases have very low density due to negligible intermolecular forces. Gases exert pressure. Gases do not have definite shape and volume like solids and liquids. Thermal energy of gases is much greater than molecular attraction. The gas laws. Boyle's law. Pressure-volume relationship. The volume of a given mass of a gas is inversely proportional to its pressure at constant temperature. Mathematical interpretation of the law. Volume is inversely proportional to pressure at constant temperature and mass. B is equal to K into 1 by P, where K is constant of proportionality. PV is equal to K is equal to constant. Let V1 be the volume of given mass of a gas having pressure P1 at temperature T. Now, if the pressure is changed to P2 at same temperature, then the volume changes to V2. The quantitative relationship between four variables P1, V1, P2 and V2 is P1 V1 is equal to P2 V2 at constant temperature and mass. Graphical representation of Boyle's law. It shows the plot of V versus P at a particular temperature. It shows as P increases, V decreases. It shows the plot of PV versus P at particular temperature. It indicates that the PV values remains constant in spite of a regular increase in P. The curve obtained by plotting PV against P at a particular temperature is called isotherm. The higher curve corresponds to a higher temperature. It shows the variation of P against 1 by V. The straight line indicates that 1 by V regularly increases with the increase in P. Charles' law, temperature-volume relationship. Statement. The volume of a given mass of a gas increases or decreases by 1 by 273.15 of its volume at 0 degrees Celsius for each degree rise or fall of temperature provided pressure is kept constant. If V0 is the volume of a given mass of a gas at 0 degrees Celsius, then V1, the volume of a gas at 1 degree Celsius is equal to V0 into 1 plus 1 by 273.15. Vt, the volume of gas at T degrees Celsius is equal to V0 into 1 plus T by 273.15. The lowest possible temperature at which all the gases are supposed to occupy zero volume is called absolute zero. A scale of temperature based upon this choice of zero is called absolute scale of temperature. This scale is also known as Kelvin scale of temperature. Charles' law can also be stated as the volume of the given mass of a gas at constant pressure is directly proportional to the temperature on Kelvin scale. Volume is directly proportional to the temperature at constant pressure and mass. V is equal to K1T, where K1 is constant of proportionality. Let V1 be the volume of a certain mass of a gas at temperature T1 and at pressure P. If temperature is changed to T2 keeping pressure constant, the volume changes to V2. The relationship between four variables V1, T1, V2 and T2 is V1 by T1 is equal to V2 by T2 at constant pressure and mass. Graphical representation of Charles' law. Each line of the volume versus temperature graph is called isobar. Gay-Lussac's law, pressure-temperature relationship. This law states that pressure of a given mass of a gas is directly proportional to the Kelvin temperature at constant volume. Mathematically, pressure is directly proportional to temperature at constant volume and mass. P by T is equal to K2. Let P1 be the pressure of a certain mass of a gas at temperature T1 and having a volume V. Now, if temperature is changed to T2 at the same volume so that the corresponding pressure becomes P2, then according to the law, P1 by T1 is equal to P2 by T2. Volume and mass remains constant. Graphical representation of Gay-Lussac's law. Each line of this graph is called isochore. Avogadro's law, volume-amount relationship. This law states that equal volume of all the gases under similar conditions of temperature and pressure contain equal number of molecules. Mathematically, volume is directly proportional to the number of moles of gas. V is equal to K3N, where K3 is constant of proportionality. The number of molecules in 1 mole of gas is 6.023 into 10 raised to the power 23 and is known as Avogadro's constant. The number of moles can be defined as N is equal to M by M, where M is equal to mass of a gas under investigation and M is equal to molar mass. Ideal gas equation. A gas which obeys the gas law strictly is called an ideal gas. The combination of Boyle's law, Charles' law and Avogadro's law leads to the development of the equation which we called ideal gas equation. It is given as PV is equal to nRT, where R is the constant of proportionality which is independent of the amount as well as nature of gas and is known as universal gas constant. Its value is 8.31 joule per Kelvin per mole. P is the pressure of fixed amount of gas. V is the volume of fixed amount of gas. T is the temperature of fixed amount of gas. N is the number of moles of gas. If temperature, volume and pressure of a fixed amount of a gas vary from T1 V1 and P1 to T2 V2 and P2, then we can write P1 V1 by T1 is equal to P2 V2 by T2. This equation is called combined gas law. Standard temperature and pressure, STP. For gases, the standard temperature is taken as 0 degrees Celsius or 273.15 Kelvin and standard pressure as 1 bar or 10 raised to the power 5 Pascal. At STP, molar volume of an ideal gas or a combination of ideal gases is 22.71098 liter per mole. Another unit for pressure measurement is torr. 1 torr is equal to 133.322 Pascal. Example: a sample of nitrogen gas occupies a volume of 320 centimeter cube. At STP, calculate its volume at 66 degrees Celsius and 84,000 Pascal pressure. Solution: given P1 is equal to 10 raised to the power 5 Pascal, P2 is equal to 84,000 Pascal, V1 is equal to 320 centimeter cube, T1 is equal to 273.15 Kelvin, T2 is equal to 66 degrees Celsius is equal to 66 plus 273.15 Kelvin is equal to 339.15 Kelvin. We have to find V2. So, according to gas equation, P1 V1 by T1 is equal to P2 V2 by T2. Hence, V2 is equal to P1 V1 T2 by T1 P2 is equal to 10 raised to the power 5 into 320 into 339.15 divided by 273.15 into 84,000 is equal to 473 centimeter cube. Density and molar mass of a gaseous substance. Molar mass of the gas can be found by the formula M is equal to D into R into T by P, where D is equal to M by V is the density of the gas, M is mass of gas, V is the volume of the gas, R is the universal gas constant, T is the temperature of the gas, P is the pressure of the gas. Dalton's law of partial pressures. At constant temperature, the pressure exerted by the mixture of two or more non-reacting gases enclosed in a definite volume is equal to the sum of the individual pressures which each gas would exert if present alone is the same volume. The individual pressures of gases are known as partial pressures. If P is the total pressure of the mixture of non-reacting gases at temperature T and volume V, and P1, P2, P3 represents the partial pressures of the gases, then P is equal to P1 plus P2 plus P3 plus so on, where T and V are constants. Suppose we have 3 containers of capacity 1 liter each, one containing X mole of nitrogen, the other Y mole of oxygen, and third having a mixture of X moles of nitrogen and Y moles of oxygen. all the three containers are kept at the same temperature. Now, if the manometer attached to first container shows a pressure P1 and that attached to second container shows a pressure P2, then pressure in the third container is P1 plus P2. The pressure of the water vapors is a constant at a particular temperature and is known as aqueous tension at that temperature. Pressure of a dry gas can be calculated by subtracting aqueous tension from a total pressure. P dry gas is equal to P minus aqueous tension. Partial pressure in terms of mole fraction. Mole fraction is the ratio of the number of mole of the component to the total number of moles. Consider a mixture of two gases A and B with PA and PB as their respective partial pressure in a vessel of volume V at temperature T. Then, PA is equal to NART by V. PB is equal to NBRT by V. The partial pressure of gas A and B can be expressed as PA is equal to XA into P. PB is equal to XB into P, where P is the total pressure, XA and XB are the mole fraction of gas A and B. Thus, partial pressure of a gas in a mixture is equal to the product of its mole fraction and total pressure of the mixture. Kinetic molecular theory of gas. Postulates of kinetic theory of gas are: all gases are made up of very large numbers of extremely small particles called molecules. The molecules are separated from one another by large spaces so that the actual volume occupied by the molecules is negligible as compared to the total volume of the gas. The molecules are not at rest but possess rapid random motion. During this motion, they collide with one another and also against the walls of the container. The pressure of the gas is due to the bombardment of the gas molecules against the wall of the container. The collisions of the molecules with each other and with the walls of the container are perfectly elastic. That is, there is no loss or gain of kinetic energy. However, there may be redistribution of energy during such collisions. There are no attractive forces between the molecules of the gas. They are completely independent of each other. At any instant, different molecules possess different velocities and hence different energies. However, the average kinetic energy of the molecules is directly proportional to the absolute temperature. Behavior of real gases. Deviation from ideal gas behavior. We show the deviation of real gas from the ideal behavior by introducing compressibility factor. Z can be expressed as Z is equal to PV by nRT. In case of ideal gas, PV is equal to nRT. Hence, Z is equal to 1. In case of real gas, PV not equals to Z nRT. Hence, Z not equals to 1. Thus, in a case of real gas, the value of Z can be less than 1 or greater than 1. When Z is less than 1, it refers to negative deviation. It implies that the gas is more compressible than expected from ideal behavior. When Z greater than 1, it refers to positive deviation. It implies that the gas is less compressible than expected from ideal behavior. Cause of deviations from ideal behavior is due to two faulty assumptions of kinetic theory of gas, that are: the volume occupied by gas molecules is negligibly small as compared to the total volume occupied by the gas. The forces of attraction between gas molecules are negligible. Van der Waals equation. In 1873, Van der Waals modified the gas equation to make it applicable for real gases as well. That is, P plus An square by V square into V minus Nb is equal to nRT. The constants A and B are also called Van der Waals constants. Liquefaction of gases. Liquefaction of gas can be achieved by decrease of temperature and by increase of pressure. Concept of critical temperature. At low temperature 13.1 degrees Celsius, CO2 exists as gas at low pressure as shown by point A. As the pressure is increased, the volume of gas decreases along the curve AB. At point B, liquefaction starts. Hence, volume decreases rapidly along the line BC. At the point C, the liquefaction is complete. Now further increase of pressure has very little effect upon the volume because liquids are very little compressible. Hence, a steep curve CD is obtained. Thus, along the portion AB, carbon dioxide exists only as gas, along the portion CD only as liquid, and along the portion BC, the liquid and the vapor are in equilibrium with each other. The isotherm EFGH at 21.5 degrees Celsius is smaller to that at 13.1 degrees Celsius, except that the horizontal portion over the liquefaction occur is shorter. In the isotherms above 31.1 degrees Celsius, the horizontal portion completely disappears. This shows that above 31.1 degrees Celsius, the liquefaction of the gas does not take place at all. However, high pressure may be applied. The point X is called critical point and temperature corresponding to point X is called critical temperature. The critical temperature of the gas may be defined as the temperature about which it cannot be liquefied by application of pressure. The pressure required to liquefy the gas at critical temperature is called critical pressure. The volume of 1 mole of the gas at critical temperature and critical pressure is called critical volume. Liquid state. In liquid state, particles are close together and have quite strong intermolecular forces. The liquids are neither rigid nor do they possess definite shape. Vapor pressure. The vapors of liquid collide with each other as well as with the walls of the container and exert pressure. The pressure exerted by vapors on the wall of the container is called vapor pressure. Vapor pressure is directly proportional to the temperature. It is independent of the amount of liquid. The pressure exerted by the vapor when they are in equilibrium with liquid in a closed container is called equilibrium vapor pressure. The temperature at which the vapor pressure of a liquid is equal to external pressure is called boiling point of liquid. Surface tension. A molecule within the bulk of liquid is uniformly attracted in all directions by the neighboring molecules. Therefore, the net force of attraction acting on such a molecule is almost zero. However, a molecule at the surface of liquid has no upper molecules to participate in attraction. This creates imbalance of forces at the surface of the liquid. Consequently, the molecules at the surface experience a resultant inward pull. For a plane surface, the force acting parallel to the surface and perpendicular to a line of unit length anywhere in the surface is called surface tension. It is represented by gamma and its unit is dynes per centimeter or Newton per meter. In order to increase the surface area of the liquid, some energy has to be supplied against the inward pull. This is referred to as surface energy. Thus, surface energy is the energy required or work required to be done to increase the surface area of the liquid by a unit amount. It is expressed in joule per meter square or Newton per meter. Viscosity. Viscosity implies resistance to flow. It is well-known fact that some liquids such as honey, castor oil, glycerine, etc. flow slowly, whereas other like water, petrol, ethanol, etc. flow rapidly. This means that every liquid has some internal resistance to flow, which is referred to as viscosity. Liquids which flow slowly are said to be more viscous than the liquids which flow rapidly. The force of friction F between two cylindrical layers, each having area A square centimeter separated by a distance x centimeter and having a velocity difference of nu centimeter per second is given by F is equal to eta A nu by x, where eta is the coefficient of viscosity. Now, if A is equal to 1 centimeter square, nu is equal to 1 centimeter per second and x is equal to 1 centimeter, then F is equal to eta. Thus, coefficient of viscosity may be defined as force of friction required to maintain velocity difference of 1 centimeter per second between two parallel layers 1 centimeter apart and having an area of 1 centimeter square. SI unit of viscosity is Newton per meter square second or 1 poise. Did you know? Graphite enters different states of matter in ultra-fast experiment. For the first time, scientists have seen an X-ray irradiated mineral go to two different states of matter in about 40 femtoseconds. A femtosecond is 1/400th of a second. Ultra-fast phase transitions from solid to liquid and plasma states are important in the development of new material synthesis techniques, ultra-fast imaging and high energy density science. Summary. Let us summarize what we have learnt. The force of attraction between molecules which keep molecules together are called intermolecular forces. Hydrogen bond is defined as the electrostatic force of attraction which exists between the covalently bonded hydrogen atom of one molecule and electronegative atom of the other molecule. The energy which moves the molecules apart is called thermal energy. Boyle's law states that the volume of a given mass of a gas is inversely proportional to its pressure at constant temperature. PV is equal to K is constant. Charles' law states that the volume of a given mass of a gas at constant pressure is directly proportional to the temperature on Kelvin scale. V by T is equal to K1 is constant. Gay-Lussac's law states that pressure of a given mass of a gas is directly proportional to the Kelvin temperature at constant volume. P by T is equal to K2 is constant. Avogadro's law states that equal volumes of all gases under similar conditions of temperature and pressure contain equal number of molecules. V by N is equal to K3 is constant, where N is the number of moles of gas. Ideal gas equation is given as PV is equal to nRT, where R is the universal gas constant. Dalton's law of partial pressures states that at constant temperature, the pressure exerted by a mixture of two or more non-reacting gases enclosed in a definite volume is equal to the sum of the individual pressures which each gas would exert if present alone in the same volume. Liquefaction of gas can be achieved by decrease of temperature and by increase of pressure. The pressure exerted by vapors on the walls of the container is called vapor pressure. For a plane surface, the force acting parallel to the surface and perpendicular to a line of unit length anywhere in the surface is called surface tension. It is represented by gamma and its unit is dynes per centimeter or Newton per meter. Every liquid has some internal resistance to flow, which is referred to as viscosity.
Introduction. Total mass of the products remains equal to the total mass of the reactants. H2 plus Cl2 gives 2HCl. A chemical compound always contains same elements combined together in same proportion of mass. Ice H2O 1:8. River H2O 1:8. Sea H2O 1:8. Objectives. At the end of this lesson, you will be able to determine significant figures, explain various laws of chemical combination, describe the terms atomic mass, average atomic mass, molecular mass, and formula mass, mole. Calculate the mass percent of different elements constituting a compound. Determine empirical formula and molecular formula for a compound from the given experimental data. Perform the stoichiometric calculations. Dimensional analysis. Often while calculating, there is a need to convert units from one system to other. The method used to accomplish this is called factor label method or unit factor method or dimensional analysis. Laws of chemical combination. The combination of elements to form compounds is governed by the following 5 basic laws. Law of conservation of mass. It states that matter can neither be created nor destroyed. For example, reaction of one molecule zinc react with one molecule of sulfur to form 1 molecule of zinc sulfide. Law of definite proportions. This law was given by a French chemist, Joseph Proust. He stated that a given compound always contains exactly the same proportion of elements by weight. In formation of water compound, the ratio of the mass of hydrogen to the mass of oxygen is always 1:8, whatever the source of water. Law of multiple proportions. This law was proposed by John Dalton in 1803. According to this law, if two elements can combine to form more than one compound, the masses of one element that combine with the fixed mass of the other element are in the ratio of small whole numbers. Example: 100 grams of carbon may react with 133 grams of oxygen to produce CO, or with 266 grams of oxygen to produce CO2. The ratio of the masses of oxygen that can react with 100 grams of carbon is 266:133, or approximately 2:1, a ratio of small whole numbers. Gay-Lussac's law of gaseous volumes. This law was given by Gay-Lussac in 1808. He observed that when gases combine or are produced in a chemical reaction, they do so in a simple ratio by volume, provided all gases are at same temperature and pressure. Thus, 100 ml of hydrogen combine with 50 ml of oxygen to give 100 ml of water vapor. Hydrogen plus oxygen gives water. 100 ml plus 50 ml gives 100 ml. Thus, the volumes of hydrogen and oxygen which combine together, that is 100 ml and 50 ml, bear a simple ratio of 2:1. Avogadro law. In 1811, Avogadro proposed that equal volumes of gases at the same temperature and pressure should contain equal number of molecules. Avogadro made a distinction between atoms and molecules, which is quite understandable in the present time. If we consider again the reaction of hydrogen and oxygen to produce water, we see that 2 volumes of hydrogen combine with 1 volume of oxygen to give 2 volumes of water without leaving any unreacted oxygen. Dalton's atomic theory. Dalton proposed the following points. 1. Matter consists of indivisible atoms. 2. All the atoms of a given element have identical properties including identical mass. Atoms of different elements differ in mass. 3. Compounds are formed when atoms of different elements combine in a fixed ratio. 4. Chemical reactions involve reorganization of atoms. These are neither created nor destroyed in a chemical reaction. Atomic mass and average atomic mass. One atomic mass unit is defined as a mass exactly equal to 1/12 the mass of one carbon-12 atom. And 1 AMU is equal to 1.66056 into 10 raised to the power minus 24 gram. Mass of an atom is equal to 1.6736 into 10 raised to the power minus 24 gram of hydrogen. Thus, in terms of AMU, the mass of each atom is equal to 1.6736 into 10 raised to the power minus 24 upon 1.66056 into 10 raised to the power minus 24, which is equal to 1.0078 AMU, which equals 1.0080 AMU. Similarly, the mass of oxygen 16O atom would be 15.995 AMU. When we use atomic masses of elements in calculations, we actually use average atomic masses of elements. Example: the average atomic mass of carbon isotopes will come out to be 0.98892, 12U plus 0.01108, 13.00335U plus 2 into 10 minus 12, 14.00317U is equal to 12.011U. Molecular mass and formula mass. Molecular mass is the sum of atomic masses of the elements present in a molecule. It is obtained by multiplying the atomic mass of each element by the number of its atoms and adding them together. Example, molecular mass of methane. CH4 is equal to 12.011U plus 4 into 1.008U is equal to 16.043U. Similarly, molecular mass of water H2O is equal to 2 into atomic mass of H plus 1 into atomic mass of O is equal to 2 into 1.008U plus 16.00U, which is equal to 18.02U. The formula such as NaCl is used to calculate the formula mass instead of molecular mass, as in the solid state sodium chloride does not exist as a single entity. Thus, formula mass of sodium chloride is equal to atomic mass of sodium plus atomic mass of chlorine is equal to 23.0U plus 35.5U, which is equal to 58.5U. Percentage composition. The percent composition of a compound is a relative measure of the mass of each different element present in the compound. Calculate the percentage composition by weight mass of element is equal to total mass of element present divided by molecular mass into 100. Empirical formula for molecular formula. Empirical formula of a compound shows the ratio of elements present in a compound. Molecular formula of a compound shows how many atoms of each element are present in a molecule of the compound. The empirical formula mass of a compound refers to the sum of the atomic masses of the elements present in the empirical formula. The molecular mass, formula weight, or molecular weight of a compound is a multiple of the empirical formula mass. Mm is equal to N into empirical formula mass. Empirical formula can be calculated from the percentage or percent composition of a compound. Examples of empirical and molecular formula. If carbon and hydrogen are present in a compound in a ratio of 1:2, the empirical formula for the compound is CH2. The empirical formula mass of this compound is 12.0 plus 2 into 1.0, which is equal to 14.0 G per mole. If we know the molecular mass of the compound is 28.0 G per mole, then we can find the molecular formula for the compound. Mm is equal to N into empirical formula mass. 28.0 is equal to N into 14.0. So, N is equal to 2. So, the molecular formula for the compound is 2 into empirical formula, that is 2 into CH2, which is C2H4. There are many compounds that can have the empirical formula CH2. These include C2H4, ethene or ethylene, molecular mass is equal to 28.0 and N is equal to 2. C3H6, propene or propylene, molecular mass is equal to 42.0 and N is equal to 3. Stoichiometry and stoichiometric calculations. Stoichiometry deals with the calculation of masses, sometimes volumes also, of the reactants and the products involved in a chemical reaction. Example, CH4 plus 2O2 gives CO2 plus 2H2O. The coefficients 2 for O2 and H2O are called stoichiometric coefficients. Similarly, the coefficient for CH4 and CO2 is 1 in each case. Thus, according to the above chemical reaction, 1 mole of CH4 reacts with 2 moles of O2 to give 1 mole of CO2 and 2 moles of H2O. 22.4 of CH4 reacts with 44.8 of O2 to give 22.4 of CO2 and 44.8 of H2O. 16 gram of CH4 reacts with 2 into 32 gram of O2 to give 44 gram of CO2 and 2 into 18 gram of H2O. Mole concept and molar masses. 1 mole is the amount of a substance that contains as many particles or entities as there are atoms in exactly 12 gram or 0.012 kg of the 12 carbon isotope. 1 mole is known as Avogadro constant, denoted by Na. Hence, so many entities, atoms, molecules or any other particle constitute 1 mole of a particular substance. Or we can say that 1 mole of H atoms is equal to 6.022 into 10 raised to the power 23 atoms. 1 mole of water molecules is equal to 6.022 into 10 raised to the power 23 water molecules. The mass of 1 mole of a substance in grams is called its molar mass. Molar mass of water is equal to 18.02 gram. Molar mass of sodium chloride is equal to 58.5 gram. Reactions in solutions. The concentration of a solution or the amount of substance present in its given volume can be expressed in any of the following ways. 1. Mass percent or weight percent. 2. Mole fraction. 3. Molality. 4. Molarity. Terms expressed concentrations. Percent composition by mass. We can consider percent by mass or weight percent as it is sometimes called in 2 ways. The parts of solute per 100 parts of solution. The fraction of a solute in a solution multiplied by 100. Percentage by mass is equal to mass of solute upon mass of solution into 100. Molarity. Molarity tells us the number of moles of solute in exactly 1 liter of solution. Note that molarity is spelled with an R and is represented by a capital M. Molarity is equal to mass of solute upon volume of solution, liter. Molality. Molality tells us the number of moles of solute dissolved in exactly 1 kilogram of solvent and represented by a lowercase m. Molality is equal to mass of solute upon mass of solution, kilogram. Mole fraction. The mole fraction, X, of a component in a solution is the ratio of the number of moles of that component to the total number of moles of all components in the solution. XA is equal to moles of A upon moles of A plus moles of B. XB is equal to moles of B upon moles of A plus moles of B. Did you know, according to modern atomic theory, atom is divisible? Same atom may have different atomic masses like 1H, 2H and 3H. Different atoms may have same atomic mass like 40Ca and 40Ar. Atom is the smallest particle that takes part in a chemical reaction. The mass of an atom can be changed into energy. Summary. Let us summarize what we have learned. All these laws led to the Dalton's atomic theory, which states that atoms are building blocks of matter. The atomic mass of an element is expressed relative to 12 carbon isotope of carbon, which has an exact value of 12. The molecular mass of a molecule is obtained by taking sum of the atomic masses of different atoms present in a molecule. The quantitative study of the reactants required or the products formed is called stoichiometry. The amount of substance present in a given volume of a solution is expressed in mass percent, mole fraction, molarity, and molality. The number of atoms, molecules, or any other particles present in a given system is expressed in the terms of Avogadro constant 6.022 into 1023. This is known as 1 mole of the respective particles or entities. Introduction. Chemistry deals with the composition, structure, and properties of matter. These aspects can be best described and understood in terms of basic constituents of matter, atoms, and molecules. For example, medicines, vitamins, tonic, fertilizers, industry, polymers, soaps, detergents, waterproof clothes, and fireproof building material all are related to chemistry. Objectives. At the end of this lesson, you'll be able to understand and appreciate the role of chemistry in different spheres of life. Explain the characteristics of 3 states of matter. Classify different substances into elements, compounds, and mixtures. Define SI base units. Differentiate between precision and accuracy. Importance of chemistry. Chemistry plays an important role in meeting human needs for food, healthcare products, and other materials aimed at improving the quality of life. This is exemplified by the large-scale production of a variety of fertilizers, improved varieties of pesticides and insecticides. Similarly, many life-saving drugs, such as cisplatin and Taxol, are effective in cancer therapy, and AZT, zidothiamidine, used for helping AIDS victims, have been isolated from plant and animal sources or prepared by synthetic methods. Nature of matter. Matter is any material substance with mass and volume. Everything around us, for example, book, pen, pencil, water, air, all living beings, etc., are composed of matter. Physical states of matter. Matter can exist in 3 physical states like solid, liquid, and gas. Solids have definite volume and definite shape. Liquids have definite volume but not the definite shape. They take the shape of the container in which they are placed. Gases have neither definite volume nor definite shape. They completely occupy the container in which they are placed. Classification of matter. At the macroscopic or bulk level, matter can be classified as mixtures or pure substances. Mixtures. Many of the substances present around us are mixtures. For example, sugar solution in water, air, tea, etc. are all mixtures. A mixture contains 2 or more substances present in it in any ratio which are called its components. For example, coffee contains a complex mixture of chemical compounds. Types of mixtures. A mixture may be classified into homogeneous and heterogeneous. Homogeneous mixture. In a homogeneous mixture, the components completely mix with each other and its composition is uniform throughout. Example, mixture of sugar in water, mixture of salt in water, mixture of copper sulfate in water. Heterogeneous mixture. In heterogeneous mixtures, the composition is not uniform throughout and sometimes the different components can be observed. Example, the mixtures of salt and sugar, grains and pulses along with some dirt, often stone pieces. Pure substance. Pure substances have characteristics different from the mixtures. They have fixed composition, whereas mixtures may contain the components in any ratio and their composition is variable. Example, copper, silver, gold, water, glucose. Classification of pure substance. Pure substances can be further classified into elements and compounds. An element consists of only one type of particles. These particles may be atoms or molecules. Example, hydrogen, helium, carbon, sodium, copper, silver, oxygen, etc. Compound. When two or more atoms of different elements combine, the molecule of a compound is obtained. The examples of some compounds are water, ammonia, carbon dioxide, sugar, etc. Properties of matter. Every substance has unique or characteristic properties. These properties can be classified into two categories: physical properties and chemical properties. Physical properties are those properties which can be measured or observed without changing the identity or the composition of the substance. Examples, color, odor, melting point, boiling point, density, etc. The measurement or observation of chemical properties require a chemical change to occur. Examples, characteristic reactions of different substances. These include acidity or basicity, combustibility, etc. The International System of Units, SI. The SI system has 7 base units, and these units pertain to the 7 fundamental scientific quantities. The other physical quantities such as speed, volume, density, etc. can be derived from these quantities. The definitions of the SI base units are given in table. The SI system allows the use of prefixes to indicate the multiples or submultiples of a unit. Mass and weight. Mass of a substance is the amount of matter present in it, while weight is the force exerted by gravity on an object. The mass of a substance is constant, whereas its weight may vary from one place to another due to change in gravity. The mass of a substance can be determined very accurately in the laboratory by using an analytical balance. Volume and density. Volume has the units of length raised to the power 3. So, in SI system, volume has units of meter cube. In chemistry laboratories, smaller volumes are used. Hence, volume is often denoted in centimeter cube or decimeter cube units. A common unit, liter, L, which is not an SI unit, is used for measurement of volume of liquids. 1 liter is equal to 1000 milliliter. 1000 centimeter cube is equal to 1 decimeter cube. In the laboratory, volume of liquids or solutions can be measured by graduated cylinder, burette, pipette, etc. A volumetric flask is used to prepare a known volume of a solution. Density of a substance is its amount of mass per unit volume. So, SI units of density can be obtained as follows. SI unit of density is equal to SI unit of mass upon SI unit of volume, which is equal to kgm raised to the power minus 3 or gcm raised to the power minus 3. Temperature. There are 3 common scales to measure temperature: degree Celsius, degree Fahrenheit, and Kelvin. Here K is the SI unit. Generally, the thermometer with Celsius scale are calibrated from 0 degree Celsius to 100 degree, whereas these two temperatures are the freezing point and the boiling point of water respectively. The Fahrenheit scale is represented between 32 degrees to 212 degrees. The temperatures on two scales are related to each other by the following relationship. Degree Fahrenheit is equal to 9/5 degrees Celsius plus 3. The Kelvin scale is related to Celsius scale as follows. Kelvin is equal to degree Celsius plus 273.1. Significant figures. Significant figures are meaningful digits which are known with certainty. The uncertainty is indicated by writing the certain digits and the last uncertain digit. Rules for determining the number of significant figures. All non-zero digits are significant. Example, in 285 centimeter, there are 3 significant figures, and in 0.25 milliliter, there are 2 significant figures. Zeros preceding to first non-zero digit are not significant. Such zero indicates the position of decimal point. Thus, 0.03 has one significant figure and 0.0052 has 2 significant figures. Zeros between two non-zero digits are figures. Zeros at the end or right of a number are significant provided they are on the right side of the decimal point. Example, 0.200 gram has 3 significant figures. But if otherwise, the zeros are not significant. For example, 100 has only one significant figure. Exact numbers have an infinite number of significant figures. For example, in 2 balls or 20 eggs, there are infinite significant figures, as these are exact numbers and can be represented by writing infinite number of zeros after placing a decimal, that is, 2 is equal to 2.0000 or 20 is equal to 20.00000. 4.01 into 10 raised to the power 2 has 3 significant figures, and 8.256 into 10 raised to the power minus 3 has 4 significant figures. Addition, subtraction, multiplication and division of significant figures. Points for rounding of the numbers. 1. If the rightmost digit to be removed is more than 5, the preceding number is increased by 1. Example, 1.386. If we have to remove 6, we have to round it to 1.39. 2. If the rightmost digit to be removed is less than 5, the preceding number is not changed. Example, 4.334. If 4 is to be removed, then the result is rounded up to 4.33. 3. If the rightmost digit to be removed is 5, then the preceding number is not changed if it is an even number, but it is increased by 1 if it is an odd number. Example, if 6.35 is to be rounded by removing 5, we have to increase 3 to 4, giving 6.4 as the result. However, if 6.25 is to be rounded off, it is rounded off to 6.2. Did you know the phlogiston theory viewed phlogiston as a component of all matter? The burning of a material was considered to be the escaping of phlogiston from the matter. If a material did not burn, it was considered to contain no phlogiston. The phlogiston theory. In this theory, burning was considered to be the escape of phlogiston into the air. Smelting combined phlogiston-poor ore with phlogiston from a fire to make a metal. Metal rusting was considered to be the slow escape of phlogiston from a metal into the air. Summary. Let us summarize what we have learned. All substances contain matter which can exist in 3 states: solid, liquid, or gas. Matter can also be classified into elements, compounds, or mixtures. The measurements of quantities in chemistry are spread over a wide range of 10 to 31 to 10 plus 23. Hence, a convenient system of expressing the number in scientific notation is used. The uncertainty is taken care of by specifying the number of significant figures in which the observations are reported. The combination of different atoms is governed by basic laws of chemical combination.
Introduction. Sumit and his mother are standing at the window and watching outside. The weather is looking good and there is a probability of first rain of the season. Suddenly, rain starts. Sumit requests his mother to let him go outside and enjoy the rain. But his mother didn't allow him to go outside in the rain. She said that the very first rain may be an acid rain, and an acid rain is harmful for us. Sumit didn't have any idea about that and asked her, "What is acid rain?" She replied him that atmosphere have many polluted particles like carbon, sulfur and nitrogen. These particles make redox reactions with water drops and turn them into acid rain. Students, redox reactions are all around us. Burning of fuel, digestion of food, decay of organic substances are few examples of redox reaction. Today, we will more discuss about the redox reactions. Objectives. At the end of this lesson, you will be able to define redox reactions. Familiar about classical idea of redox reactions. Understand electronic concept of oxidation and reduction reaction. Know simultaneous occurrence of oxidation and reduction. Calculate oxidation number. Define oxidation and reduction in terms of oxidation number. Understand types of redox reactions. Do balancing by ion-electron method and oxidation number method. Analyze redox reaction and electrode process. Define electrochemical cell. Definition. In our daily life, we come across processes like rusting of iron, fading of the color of the clothes, burning of the combustible substance such as cooking gas, wood, coal, etc. All such processes fall in the category of specific type of chemical reactions called reduction-oxidation or redox reactions. Classical idea of redox reactions. Oxidation. It is a process of addition of oxygen or any electronegative radical or removal of hydrogen or any electropositive radical. Reduction. It is a process of addition of hydrogen or any electropositive radical or removal of oxygen or any electronegative radical. Let us take some examples for better understand the redox reaction. Reaction of PbO and carbon. Here, oxygen is being removed from lead oxide and is being added to carbon. Thus, PbO is reduced while C is oxidized. Reaction of H2S and Cl2. Here, hydrogen is being removed from hydrogen sulfide and is being added to chlorine. Thus, H2S is oxidized and Cl2 is reduced. Electronic concept of oxidation and reduction reaction. Electrochemical reactions occur as a result of transference of electrons from one species to the other. Consider an example. If magnesium is burnt in oxygen, it gets oxidized to magnesium oxide. In the formation of magnesium oxide, 2 electrons from magnesium atom are transferred to oxygen atom. Oxidation is a process in which an atom or a group of atoms taking part in chemical reaction lose one or more electrons. The loss of electrons result in the increase of positive charge or decrease of negative charge of the species. The species which undergo the loss of electrons during the reactions are called reducing agents. MnO4, 3 negative, Fe2 plus and CO are reducing agents in these examples. Reduction is a process in which an atom or a group of atoms taking part in chemical reaction gains one or more electrons. The gain of electrons results in the decrease of positive charge or increase of negative charge of the species. The species which undergo gain of electrons during the reactions are called oxidizing agents. Ag+, Fe3+, FeCN6(3) negative are oxidizing agents in these examples. Simultaneous occurrence of oxidation and reduction. Since oxidation involves loss of electrons and reduction involves gain of electrons, it is evident that if one substance loses electrons, another substance at the same time must gain electrons. This means that in any process, oxidation can occur only if reduction is also taking place side by side and vice versa. During the redox reaction, there is transference of electrons from the reducing agent to the oxidizing agent. In this reaction, zinc atoms lose electrons and are oxidized to zinc ions, whereas cupric ions gains electrons and are reduced to copper atoms. Here, cupric ions act as oxidizing agent and zinc atoms act as reducing agent. Every redox reaction can be split up into two half reactions. One representing loss of electrons, known as oxidation half reaction. Other representing gain of electrons, known as reduction half reaction. The reaction can be split up into half reactions as SN2 positive gives rise to SN4 positive plus 2 electrons. This equation is oxidation half reaction. And 2Hg2 positive plus 2 electrons gives rise to Hg2 2 positive. This equation is reduction half. Oxidation number. Oxidation number of the element is defined as the residual charge which its atom has or appears to have when all other atoms from the molecules are assumed to be removed as ions by counting the shared electrons with more electronegative atoms. Consider an example of hydrogen chloride molecule. Chlorine is more electronegative than hydrogen. Therefore, the shared pair is counted towards chlorine atom. Chlorine gets one extra electron and acquires a unit negative charge. Hence, oxidation number of chlorine is -1. On the other hand, hydrogen atom without electron has a unit positive charge. Hence, oxidation number of hydrogen in hydrogen chloride is +1. General rules for assigning oxidation number to an atom. Rule first. The oxidation number of the element in the free or elementary state is always 0, irrespective of its allotropic form. Rule second. The oxidation number of the element in monoatomic ion is equal to the charge on the ion. Rule third. The oxidation number of fluorine is always -1 in all its compounds. Rule fourth. Hydrogen is assigned oxidation number +1 in all its compounds except in metal hydrides. In metal hydrides, the oxidation number of hydrogen is -1. Rule fifth. Oxygen is assigned oxidation number -2 in most of its compounds. Rule sixth. In polyatomic ion, the sum of oxidation numbers of all its atoms is equal to the charge on the ion. Rule 7th. In binary compounds of metal and non-metal, the metal atom has positive oxidation number, while the non-metal atom has negative oxidation number. Rule 8th. In binary compounds of non-metals, the more electronegative atoms has negative oxidation number, but less electronegative atom has positive oxidation number. Oxidation and reduction in terms of oxidation number. Oxidation is defined as a chemical process in which oxidation number of the element increases. Reduction is defined as the chemical process in which oxidation number of the element decreases. Consider the reaction between hydrogen sulfide and bromine to give hydrogen bromide and sulfur. The oxidation number of bromine decreases from 0 to -1, thus it is reduced. The oxidation number of S increases from -2 to 0, hence H2S is oxidized. Oxidizing agent is a substance which undergoes decrease in the oxidation number of one or more of its elements. Reducing agent is a substance which undergoes increase in the oxidation number of one or more of its elements. In this example, H2S is a reducing agent while Br2 is oxidizing agent. Types of redox reactions. Combination reactions. Combination reactions occurs when two reactants combine to form one product. A good example is the reaction of magnesium with air. Decomposition reaction. Decomposition reactions occur when one reactant decomposes to form two products. A good example is the reaction of mercury oxide to give elemental mercury and oxygen. Displacement reaction. Displacement reactions occur when one element displaces another element from a compound during a chemical reaction. A good example is the reaction of sodium with water. Disproportionation reaction. The reactions in which the same species gets oxidized and reduced means same species changes to its lower oxidation state and higher oxidation state are known as disproportionation reaction. In this reaction, chlorine is oxidized and reduced at the same time. Balancing by ion-electron method. Step first. Indicate the oxidation number of each atom involved in the reaction. Step second. Divide the main redox equation into two half reactions, oxidation half and reduction half. In each half reaction, balance the atoms which undergo the change in oxidation number. Step third. Add electrons to whichever side is necessary in order to make up for the difference in oxidation number in each half reaction. Step fourth. Balance oxygen atoms by addition of proper number of H2O molecules to the side which is falling short of O atoms in each half reaction. Step fifth. Balance hydrogen atoms by addition of proper number of H+ ions for acidic medium and H2O molecules for basic medium to the side which is falling short of H atoms in each half reaction. Step sixth. Equalize the number of electrons lost and gained by multiplying the half reactions with suitable integer and add them to get the final equation. Balancing by oxidation number method. Step first. First of all, ascertain whether the reaction is a redox reaction or not. In a redox reaction, oxidation number of at least one atom will change. Step second. Write the oxidation numbers of the atoms whose oxidation numbers suffer a change and write down the number of units of change. Step third. The ratio of molecules of oxidizer and reducer is equals to the change of oxidation number of reducer and change of oxidation number of the oxidizer is ascertained. If the ratio is not a simple one, make it simple. Step fourth. From the above ratio, the coefficient of the oxidizer and reducer molecules on LHS of the equation is ascertained and from which the coefficient of the product molecules on the RHS of the equation is determined. Example. Let us take an example of balancing the equations. Balance the given equation using oxidation number method. Let's see the solution. Here, the given equation is HNO3 plus H2S gives rise to NO plus S. Step 1. Firstly, we assign the oxidation number of N and S. Step 2. Now multiply the coefficient of HNO3 by 2 and H2S by 3. Step 3. Now we balance O atoms by adding 4H2O to the right side. H atoms are already balanced, hence the balanced equation is 2HNO3 plus 3H2S gives rise to 2NO plus 3S plus 4H2O. Redox reaction and electrode process. A redox reaction in which oxidation and reduction takes place in the same vessel is called direct redox reaction. In such reactions, the transference of electrons from reducing agent to oxidizing agent occurs over a very short distance. For example, if a zinc rod is immersed in copper sulfate solution taken in a beaker, a spontaneous reaction takes place and the following observations are made. Zinc rod starts dissolving and loses its mass gradually. The blue color of CuSO4 solution slowly fades. A reddish-brown precipitate of copper settles down at the bottom of the beaker. The reaction takes place with the evolution of heat. The solution remains electrically neutral. The reaction does not continue indefinitely but stops after some time. Electrochemical cell. An electrochemical cell is a device in which chemical energy is converted into electrical energy. These are also called galvanic cells or voltaic cells. Let us consider the redox reaction between zinc and CuSO4 solution. Zn and CuSO4 solution are taken in separate vessel. Zinc rod is dipped in ZnSO4 solution so that Zn and Zn2+ come in contact at the interface. Copper rod is dipped in CuSO4 solution so as to make the contact between Cu and its oxidized form Cu2+ ions. An arrangement involving contact between the oxidized and reduced form of the substance at the interface is called redox couple. The two metal rods act as electrodes and are connected by the conducting wire through a galvanometer. The two solutions are joined by the inverted U-tube known as salt bridge. The U-tube is filled with aqueous solution of some electrolyte. The electrode at which oxidation takes place is called anode, and that at which reduction takes place is called cathode. In the electrochemical cell, a salt bridge serves two very important functions. It allows the flow of current by completing the circuit. It maintains electrical neutrality. Did you know? The corrosion of metals is a naturally occurring redox reaction. The atom which gains electrons reduces its valency, therefore is reduced and is called the oxidizing agent. The atom which loses electrons increases its oxidation number, therefore is oxidized and is called the reducing agent. The redox reaction in a galvanic cell is a spontaneous reaction. For this reason, galvanic cells are commonly used as batteries. Summary. Let us summarize what we have learned. Oxidation is a process of addition of oxygen or any electronegative radical or removal of hydrogen or any electropositive radical. Reduction is a process of addition of hydrogen or any electropositive radical or removal of oxygen or any electronegative radical. The species which undergo the loss of electrons during the reactions are called reducing agents. The species which undergo gain of electrons during the reactions are called oxidizing agent. During the redox reaction, there is transference of electrons from the reducing agent to the oxidizing agent. Oxidation number is the residual charge which its atom has when all other atoms from the molecules are assumed to be removed as ions by counting the shared electrons with more electronegative atom. Decomposition reactions occur when one reactant decomposes to form two products. Displacement reactions occur when one element displaces another element from a compound during a chemical reaction. An electrochemical cell is a device in which chemical energy is converted into electrical energy.
Introduction. Today we learn isomers and concepts used in organic reaction mechanism. Anybody knows about isomers? Anyone? No? Okay, I will tell you. The organic compounds which have same molecular formula but different configurations are called isomers. The examples of isomers are dimethyl ether and ethanol. They have same molecular formula but different configuration. Teacher, what is reaction mechanism? Reaction mechanism is a sequence of steps during which chemical reactions occur. In this lesson, you will learn isomers and fundamental concepts in organic reaction mechanisms. Objectives. At the end of this lesson, you will be able to describe isomerism and its types, explain fundamental concepts in organic reaction mechanics. Isomerism. Existence of sets of two or more compounds with same molecular formulas but different configurations and hence different properties. The compounds are called isomers. Different types of isomerisms are: isomerism can be grouped into structural and stereoisomerism. Structural isomerism can be subdivided into chain isomerism, position isomerism, functional isomerism, meta-isomerism. Stereoisomerism further categorized into geometrical and optical isomerism. Structural isomerism. Structural isomers are the molecules which have the same molecular formula but have different arrangement of atoms. Chain isomerism. Chain isomers have same molecular formula but have different order in which carbon atoms are bonded to each other. Structural isomerism. Position isomerism. This isomerism is due to the difference in the position of functional group in the same chain, is termed as position isomerism. Functional group isomerism. They have same molecular formula but different functional groups. Metamerism. This isomerism arises due to non-uniform distribution of carbon atoms on either side of functional group. For example, methyl propyl ether and diethyl ether. Stereoisomerism. Stereoisomers have the same molecular formula and same connectivity, but different orientations of their atoms in space. Stereoisomerism can be grouped into geometrical and optical isomerism. Fundamental concepts in organic reaction mechanism. Organic reactions are chemical reactions involving organic compounds. The organic molecule is also termed as substrate, reacts with attacking reagent and forms intermediate and then the final product. A reaction mechanism is the step-by-step sequence of elementary reactions by which overall chemical change occurs. Fission of a covalent bond. A covalent bond may be broken by two ways: heterolytic cleavage, homolytic cleavage. In heterolytic cleavage, the bonding pair of electrons remains with one of the two fragments between which the bond is broken. For example, all carbocations have a positive charge on the carbon atom. Classification of carbocation. Primary carbocations. In this, the carbon atom which carries positive charge is attached to only one alkyl group. These are also called 1-degree carbocation. Secondary carbocations. In this, the carbon atom which carries positive charge is attached to two alkyl groups. These are also called 2-degree carbocation. Tertiary carbocations. In this, the carbon atom which carries positive charge is attached to three alkyl groups. These are also called 3-degree carbocation. Order of stability of carbocations is: a carbanion is negatively charged molecule that induces a carbon atom with negative charge. The simplest carbanion is the methide ion, can be derived from methane by a loss of proton. Homolytic cleavage. When a covalent bond breaks in such a way that each atom retains one electron of the bond, the process is called homolytic cleavage or homolysis. It often produces free radicals. The movement of single electron is shown by a fish hook arrow. Nucleophiles and electrophiles. The reagents which are electron-rich, such as chloride ion, are called nucleophiles because they seek centers of positive charge, that is, nucleus. Nucleophilicity can be defined as the tendency of an atom to donate electrons to an atom. The reagents which are electron deficient, such as carbocations, are referred to as electrophiles. Electrophilicity can be defined as tendency of an atom to accept electrons from an atom. Electron movement in organic reactions. Curly arrows are used to show the movement of electrons. The tail of the arrow indicates the location from where the electron pair is shifted, and the head of the arrow indicates the location on which the electron pair is moved. Movement of single electron is indicated by half-headed curved arrow. Electron displacement effects in covalent bonds. An attacking reagent can be positively or negatively charged. Therefore, the reagent will attack a substrate only when the substrate develops an opposite charge and the substrate can develop some polarity by the displacement of electrons. Such displacement of electrons in the substrate molecule is referred to electron displacement effect. Inductive effect. It is a permanent displacement of electrons which originate due to the difference in the electronegativity of the two atoms. Let us consider a chain of carbon atom in which the terminal carbon atom is joined to a chlorine atom. Chlorine is more electronegative than the carbon. Therefore, the electron pair in the covalent bond between the chlorine atom and C1 atom will be displaced towards the chlorine atom, due to which chlorine atom acquires a small negative charge and C1 acquires a small positive charge. Now C1 is slightly positively charged, so it attracts the electron pair, forming covalent bond between C1 and C2, due to which C2 acquires a small positive charge, but the charge is smaller than that on C1 because the effect is passed from C1 to C2. Similarly, C3 also acquires a small positive charge which is smaller than the charge on C2. This type of shift of electron along a carbon chain is known as the inductive effect. The symbol I is used to denote the inductive effect. The groups which are electron withdrawing, they are said to cause negative I effect, and the electron releasing groups are said to cause positive I effect. Resonance structure. The structure of some compounds cannot be represented by single Lewis structure. For example, toluene. Resonance structures represent two or more Lewis structures that differ only in the placement of their electrons. Organic molecule, benzene, cannot be represented by a single Lewis structure as it has alternating single and double bond. The structure of benzene ring is resonance hybrid of structures first and second, called resonating structures. Another example of resonating structures is acetate ion. The energy difference between the actual structure of resonance hybrid and the lowest energy resonance structure is called resonance energy. Following rules must be applied in writing resonating structures. The same positions of nuclei and the same number of unpaired electrons. Resonance effect. Delocalization of pi electrons over more than one atom is termed as resonance or mesomeric effect. It is symbolized by capital R or capital M. It is of two types: positive resonance effect, positive R effect. This effect is shown by the groups which release electrons to the rest of the organic molecules by delocalization of pi electrons. For example, aniline. Negative resonance effect, negative R effect. This effect is shown by the groups which withdraw electrons from the rest of the organic molecules by delocalization of pi electrons. For example, nitrobenzene. Electromeric effect, E effect. When a compound containing double or triple bond is exposed to attack by an electrophilic reagent, the electron pair is transferred completely from one atom to another. The atom to which the electron pair is transferred becomes negatively charged and the other atoms become positively charged. This is a temporary effect. As the reagent is removed, the organic molecules revert to their original state. The effect which causes temporary polarization in a substrate molecule containing a multiple bond by shifting of an electron pair from one atom to the other under the influence of an electrophilic reagent is called electromeric effect. Types of electromeric effect. Two types of electromeric effect. Positive electromeric effect, positive E effect. If the pi electrons of double or triple bond are transferred to that atom to which the reagents get attached ultimately, this effect is called positive E effect. For example, addition of acids to alkenes. Negative electromeric effect, negative E effect. If the pi electrons of double or triple bond are transferred to that atom to which the attacking reagent does not get attached, this effect is called negative electromeric effect. For example, addition of cyanide ion to the carbonyl group. Hyperconjugation. Delocalization of sigma electrons through sigma pi or sigma p overlap known as hyperconjugation. The sigma bond in conjugation with the pi bond or sigma bond in conjugation with the p orbital participates in delocalization and thus stabilizes the system. For example, in propene, there are 3 CH sigma bonds of CH3 group which are in conjugation with the pi bond. The sigma electrons are transferred to adjacent carbon-carbon bond and pi electrons are shifted to terminal CH2 carbon. 3 contributing structures are possible for propene as it has 3 CH sigma bonds. Due to participation of sigma electrons in delocalization, the bond between carbon and hydrogen does not exist in contributing structures, due to which hyperconjugation is also referred to as NO bond resonance. Did you know? In the hydrogen molecule, the sigma bond was formed by the overlap of 2 1s orbitals. Moses Gomberg is the founder of radical chemistry. Summary. Let us summarize what we have learnt. The compounds with the same molecular formulas but different configurations are called isomers. Types of isomerism are structural isomerism and stereoisomerism. A reaction mechanism is the step-by-step sequence of elementary reactions by which overall chemical change occurs. A covalent bond may be broken by heterolytic and homolytic cleavage. In heterolytic cleavage, the bonding pair of electrons remains with one of the 2 fragments between which the bond is broken. When covalent bond breaks in such a way that each atom retains 1 electron of the bond, the process is called homolytic cleavage. Nucleophilicity can be defined as the tendency of an atom to donate electrons to an atom. Electrophilicity can be defined as the tendency of an atom to accept electrons from an atom. Inductive effect is a permanent displacement of electrons which originate due to the difference in the electronegativity of 2 atoms. Delocalization of pi electrons over more than one atom is termed as resonance or mesomeric effect. The temporary polarization of an organic molecule containing a multiple bond due to the shifting of an electron pair is called electromeric effect. Delocalization of sigma electrons through sigma pi or sigma p overlap known as hyperconjugation. Introduction. Students, in the previous part we have learnt the isomerism and fundamental concepts used in the organic reaction mechanism, and today we learn the methods of purification of organic compounds. Some of the methods are sublimation, chromatography, distillation, etc.
Teacher, what is sublimation?
Sublimation is the process in which solid directly converts to vapor state without passing through liquid state upon heating. Now can anybody tell me what is chromatography?
Teacher, chromatography is a technique used to separate and analyze a mixture of chemicals.
Very good, Aryan. Now we'll study the processes of purifications in detail. In this lesson, you will learn purification of organic compounds, qualitative and quantitative analysis of organic compounds. Objectives. At the end of this lesson, you will be able to describe methods of purification of organic compounds, explain qualitative analysis of organic compounds, describe quantitative analysis. Methods of purification of organic compounds. The various methods for the purification of organic compounds are sublimation, crystallization, distillation, differential extraction, and chromatography. Sublimation. Some solids change directly from the solid state to vapor state on heating. This process is termed as sublimation. It is used to separate sublimable organic compounds from non-sublimable compounds. The impure organic compound is heated in a dish covered with perforated asbestos sheet over which an inverted funnel is placed. The stem of the funnel is filled with cotton, and on heating, the part of the solid which sublimes passes through the holes in the asbestos sheet and condense on the cooler walls of the funnel. The non-sublime impurity. Crystallization. It is the most common way of purification of organic solids. It is based on the difference in the solubility of the organic compound and the solvent in which the organic compound is mixed. The impure substance is in powder form and then heated with the solvent in a flask. The amount of solvent should be just sufficient to dissolve the substance on heating. The hot saturated solution is then filtered with the hot water funnel. The hot water circulated in the outer funnel keeps the solution hot, and crystals cannot be formed in the funnel itself. The hot filtrate is cooled in the beaker and large crystals are obtained, and then the crystals are separated from the filtrate by means of filtration. Distillation. Distillation is a method for purifying liquids and separating mixtures of liquids into their individual components. On heating the liquid mixture in a flask, the components in the liquid which have low boiling point start vaporizing. The vapors are condensed in the condenser and the resulting liquid is collected in a receiver. The components of liquid which have higher boiling point vaporize later and the liquid can be collected separately. Fractional distillation. When the boiling points of the two liquids are very close, then simple distillation does not work. In that case, a fractionating column is used, which is long tube provides obstructions to the passage of the vapors upwards and to the passage of liquid downwards. The mixture of liquids A and B with 370 Kelvin and 380 Kelvin respectively boiling points is present in the flask. On heating the flask, the vapors obtained are more of A and less of B. As the vapors rise up in the fractionating column, the partially condensed liquid flows down. The vapors of B condense faster as compared to A, and the vapors moving up richer in A. The condensed liquid flowing down strikes the vapor and it consumes molecules of B. This process is repeated throughout the fractionating column, due to which the vapors escaping through the top of the column are almost of A and the liquid left in the flask almost of B. Distillation under reduced pressure. This process is used if the liquid has a tendency to decompose near its boiling point. The main neck of the flask is fitted with long capillary tube and the side neck fitted with thermometer. This side tube is connected to a condenser which is connected to the receiver at the other end. The receiver is connected to a pump which reduces the pressure. Under reduced pressure, the liquid will boil at a low temperature and the temperature of decomposition will not be reached. For example, glycerol boils with decomposition at 563 Kelvin, but if the pressure is reduced to 12 millimeters, it boils at 453 Kelvin without decomposition. Steam distillation. This method is used to separate the substances which are steam volatile and insoluble in water. This method based on the fact that a liquid boils at a temperature when its vapor pressure becomes equal to the atmospheric pressure, and the vapor pressure of a mixture of two immiscible liquids is equal to the sum of the vapor pressures of the individual liquids. Steam is continuously passed through the compound which is required to be distilled. Steam heats the liquid and also condenses to water. After some time, the mixture of water and liquid starts boiling because the vapor pressure of the mixture becomes equal to the atmospheric pressure. The temperature at the instant is lower than the boiling point of the substance or that of water. The mixture of liquid and water is condensed and collected in a receiver which can be easily separated. Differential extraction. When organic compound is present in aqueous solution, then the organic compound is extracted by using a solvent in which organic compound is more soluble than water and the solvent is not miscible with water. If the organic compound is less soluble in a given solvent, then a very large quantity of solvent is required to extract a very small quantity of the compound. This technique is known as continuous extraction. Chromatography. Chromatography is a technique used to separate the components of a mixture to identify organic substances and examine their purity. Classification of chromatography. Adsorption chromatography, partition chromatography. Adsorption chromatography. Adsorption chromatography is based on differential absorption, that is, different compounds are absorbed on adsorbent such as solid, SiO2 gel or Al2O3 to different extent. Based on differential adsorption, there are two types: column chromatography and thin layer chromatography. Column chromatography. It is the process in which the mixture of various components, when passed through a column containing an adsorbent such as starch or charcoal, the different substances are absorbed to different degrees and thus they can be separated with the help of suitable solvent called eluent. Thin layer chromatography. It involves the spreading of the thin layer of adsorbent on a suitable support such as glass plate, etc. The glass plate is known as thin layer chromatography plate or chroma plate. The mixture to be separated is applied as a small spot from one end of the TLC plate. The glass plate is then placed in a closed jar which contains the solvent. As the solvent moves up in the jar, the components of the mixture move up along the plate to different distances depending on their degree of adsorption, and separation takes place. The relative adsorption of each component of the mixture is expressed by retention factor, that is RF value, which can be given as RF is equal to distance moved by the substance from the baseline by distance moved by the solvent from the baseline. Partition chromatography. Partition chromatography is a paper chromatography in which a special quality paper known as chromatography paper is used. Chromatography paper contains water trapped in it, which acts as the stationary phase. The chromatography paper is placed at the base with the mixture of solvents. The solvent acts as mobile phase. The solvent rises up in the paper and flows over the spot. The different components are separated according to their differing partition in the two phases. The developed paper strip is known as chromatogram. The colorless compounds may be observed either under UV light or by the use of an appropriate spray reagent. Qualitative analysis of organic compounds. Detection of carbon and hydrogen. Carbon and hydrogen are detected by heating the organic compound strongly with copper-2 oxide. The produced gases are passed through anhydrous copper sulfate and then passed into lime water in a test tube. If carbon is present, then it forms carbon dioxide, which turns the lime water milky. The reactions are as follows. Carbon in organic compound reacts with copper-2 oxide and produces copper and carbon dioxide. The produced carbon dioxide reacts with calcium hydroxide, which turns it milky, indicating the presence of carbon in organic compound. If hydrogen is present in the organic compound, then it forms water vapor, which passed over copper anhydrous sulfate turns it blue by forming CuSO4 5H2O. The reactions are as follows. Hydrogen in organic compound reacts with copper-2 oxide and produces copper and water. The produced water reacts with anhydrous copper sulfate, which turns blue by forming CuSO4 5H2O. Detection of other elements. Other elements such as nitrogen, sulfur, halogens and phosphorus in the organic compound can be detected by Lasigene's test. The elements in the organic compound fuse with the sodium metal. The reactions are as follows. When sodium reacts with various elements found in the organic compounds, then it forms sodium fusion extract. Test for nitrogen. On addition of ferrous sulfate to sodium extract, that is sodium cyanide, it produces sodium ferrocyanide. The ferric ions generated during the process react with ferrocyanide to form blue precipitate of ferric ferrocyanide. Test for sulfur. If sulfur is present in the organic compound, then it can be identified by the reaction of sodium fusion, that is sodium sulfide Na2S with sodium nitroprusside. Then, violet color indicates the presence of sulfur. Test for halogens. The presence of halogens is tested by acidifying a portion of sodium extract, that is NaX, with dilute nitric acid and adding silver nitrate. If a white precipitate is formed which is soluble in ammonium hydroxide, indicates the presence of chlorine. If a yellow precipitate is formed which is sparingly soluble in ammonium hydroxide, indicates the presence of bromine. If the formed yellow precipitate is insoluble in ammonium hydroxide, then it shows the presence of iodine. If nitrogen or sulfur has been detected, the solution must be boiled for a couple of minutes to expel HCN and H2S, which interfere with the test. Test for phosphorus. The presence of phosphorus can be detected by fusing the organic compound with sodium peroxide. The formed solution is treated with concentrated HNO3 and an excess solution of ammonium molybdate is added. A yellow precipitate indicates the presence of phosphorus. Quantitative analysis. Carbon and hydrogen. A sample of organic compound is heated to 700 degrees Celsius in a steam of pure dry oxygen and in the presence of copper-2 oxide. The hydrogen is oxidized to water and carbon to carbon dioxide. The amount of water produced is determined by passing it through anhydrous calcium chloride, and carbon dioxide is determined by passing it through solution of potassium hydroxide. The mass of hydrogen present in sample of organic compound will be 1/9, the increase in mass of the calcium chloride, and the mass of carbon will be 3/11, the increase in mass of the potassium hydroxide. Nitrogen. There are two ways for estimation of nitrogen: Dumas method and Geldel's method. Dumas method. A known mass of organic compound is heated with copper oxide in the atmosphere of carbon dioxide. Under these conditions, carbon and hydrogen are oxidized to carbon dioxide and water respectively, and nitrogen is set free. If any oxide of nitrogen is formed, it is reduced back to nitrogen by hot reduced copper. The gases produced are passed from potassium hydroxide solution through furnace. Potassium hydroxide absorbs carbon dioxide and nitrogen is collected in the upper portion of the tube. Percentage of nitrogen in organic compound whose mass is m, Gm is 28 into V into 100 divided by 22,400 into m, where V is the volume of nitrogen at STP. Geldel's method. In Geldel's method, nitrogen is estimated by ammonia gas. The organic compound is heated with sulfuric acid. Nitrogen in the organic compound is converted into ammonium sulfate. The ammonium sulfate is then heated with excess NaOH and it liberates ammonia. The produced ammonia is absorbed in standard solution of sulfuric acid. The produced ammonia can be estimated by the amount of sulfuric acid used in the reaction. It can be done by estimating the amount of sulfuric acid left after the absorption of ammonia by titrating it with standard alkali solution. The difference between the initial amount of sulfuric acid taken and the amount that left after the reaction provides the amount of acid reacted with ammonia. The percentage of nitrogen is 1.4 into m into 2 times of the difference between V and V1 by 2 divided by mass of organic compound, where V is equal to volume of H2SO4 taken in milliliters, V1 is equal to volume of NaOH in milliliters, m is equal to molarity of H2SO4. Halogens. Carius method. A known mass of organic substance is heated with fuming nitric acid and then silver nitrate is added in the tube called Carius method. The formed silver halide is separated, washed, dried and weighed. Percentage of halogen. Atomic mass of X into M1 into 100 divided by molecular mass of AgX into M, where M1 is the mass of AgX formed and M is the mass of organic compound. Sulfur. A known mass of the organic substance is heated with fuming nitric acid. The sulfur is converted into sulfuric acid. The formed sulfuric acid is precipitated as barium sulfate by adding barium chloride. The precipitate is filtered, washed, dried and weighed. Percentage of sulfur: 32 into M1 into 100 divided by 233 into M, where M1 is the mass of barium sulfate formed and M is the mass of organic compound. Phosphorus. The organic compound containing phosphorus is heated with fuming nitric acid and phosphorus is oxidized to phosphoric acid. Phosphorus is precipitated as ammonium phosphomolybdate by addition of ammonia and ammonium molybdate. Percentage of phosphorus: 31 into M1 into 100 divided by 1877 into M, where M1 is the mass of ammonium phosphomolybdate and M is the mass of organic compound. Oxygen. The percentage of oxygen in an organic compound can be determined by the method of difference. All the elements in the organic compound except oxygen are estimated and the total of their percentages subtracted from 100 to get the percentage of oxygen. The organic compound is heated in the stream of nitrogen gas. The formed mixture of gases is passed through red-hot coke and oxygen gas is converted into carbon monoxide. Now the carbon monoxide is converted into carbon dioxide by mixing iodine pentoxide into the mixture. According to chemical reactions, the percentage of oxygen can be found as 16 into mass of carbon dioxide divided by 44 into mass of organic compound into 100. Did you know? Carbon occurs in all living organisms. Carbon is a non-metal and that it can bond with itself and with many other chemical elements, forming nearly 10 million compounds. Summary. Let us summarize what we have learnt. Sublimation, crystallization, distillation, differential extraction, and chromatography are the methods for the purification of organic compounds. Carbon and hydrogen can be detected by heating the organic compound strongly with copper-2 oxide. Nitrogen, sulfur, and halogens can be detected by sodium fusion extract. The mass of hydrogen present in sample of organic compound will be 1/9, the increase in the mass of calcium chloride, and the mass of carbon will be 3/11, the increase in mass of the potassium hydroxide. Percentage of nitrogen in organic compound whose mass is mgm is 28 into V into 100 divided by 22,400 into M, where V is the volume of nitrogen at STP. Percentage of halogen in organic compound is atomic mass of X into M1 into 100 divided by molecular mass of AgX into M, where M1 is the mass of AgX formed and M is the mass of organic compound. Percentage of sulfur in organic compound is 32 into M1 into 100 divided by 233 into M, where M1 is the mass of barium sulfate formed and M is the mass of organic compound. Percentage of phosphorus in organic compound is 31 into M1 into 100 divided by 1877 into M, where M1 is the mass of ammonium phosphomolybdate and M is the mass of organic compound. Percentage of oxygen in organic compound is 16 into mass of carbon dioxide divided by 44 into mass of organic compound into 100. Introduction.
Good morning, teacher.
Good morning, students. Today we learn organic chemistry.
Teacher, what is organic chemistry?
Organic chemistry is the branch of chemistry that involves the study of carbon and hydrogen-containing compounds.
Teacher, how the carbon-carbon atoms are attached?
The carbon-carbon atoms are attached by single bond, double bond or triple bond, and the functional group present on the organic compound decides its chemical nature.
Teacher, what is functional group?
It is a group of atoms in an organic compound responsible for the chemical reactions of that compound. In this lesson, you will learn organic chemistry and some basic principles. Objectives. At the end of this lesson, you will be able to define tetravalency of carbon, describe formation of pi bond, represent organic compound through complete, condensed and bond line structural formulas, represent organic compound in 3D, classify organic compound, describe nomenclature of organic compound. Tetravalence of carbon, shapes of organic compounds. Organic chemistry is the study of hydrocarbons and other compounds regarded as derivatives of hydrocarbons. Some organic compounds may also contain elements like nitrogen, oxygen, sulfur, phosphorus, halogen, etc. besides carbon and hydrogen. The shapes of carbon compounds. A carbon atom has 4 electrons in its outermost shell, so it needs 4 more electrons to complete its octet. A carbon atom can complete its octet only by sharing its valence electrons with other atoms. As a result, carbon atom forms 4 covalent bonds by sharing valence electrons with other atoms. This is known as tetravalency of carbon. For example, methane, ethene, ethine. Carbon can participate in hybridization and form sp, sp2, sp3 hybrid orbitals. Hybridization also affects the bond length and bond enthalpy in organic compounds. The sp hybrid orbital has more s character and hence it is closer to nucleus and forms stronger bond than sp3 orbital. The sp2 hybrid orbital is an intermediate orbital between sp and sp3. Some characteristic features of pi bonds. Pi bond is formed by the overlapping of p orbitals on adjacent atoms. The p orbitals should be parallel to each other and both perpendicular to the plane of the molecule. Pi bond inhibits the free rotation of carbon-carbon double bond. Pi bond provides the electron charge cloud in the molecules which have multiple bonds. Structural representations of organic compounds. Complete, condensed and bond line structural formulas. The structure of organic compounds can be represented by Lewis or dot structure, dash structure, condensed structure, and bond line structures. The Lewis or dot structures can be simplified by using dash. Single dash represents single bond. For example, propane. Double dash represents double bond. For example, propene. Triple dash represents triple bond. For example, propyne. These structural representations are called complete structural formulas. Structural representations of organic compounds. In the condensed structural formula, each carbon atom is written separately and following each carbon atom, other atoms are listed that are bonded to that carbon atom. For example, complete structural formula. Its condensed structural formula can be written as bond line structures. In this, carbon and hydrogen atom are not shown, but only the bonds between the carbon-carbon atoms are shown in zigzag fashion. The atoms other than carbon and hydrogen are shown in the structure and the terminals denote methyl group. For example, butyl chloride, propene, cyclohexane, diethyl ether, dimethylamine. Three-dimensional representation of organic molecules. Three-dimensional structures of organic molecule on paper can be represented by using solid and dashed wedge formula. The solid wedge represents a bond projecting from the paper towards the observer. The dashed wedge represents a bond away from observer. A simple line represents a bond that lies in the plane of paper. For example, methane. Classification of organic compounds. Organic compounds can be grouped into acyclic or open chain compounds and cyclic or closed chain or ring compounds. Cyclic compounds can be further divided into homocyclic or carbocyclic compounds and heterocyclic compounds. Homocyclic can be further divided into alicyclic and aromatic compounds. Aromatic compounds can be further divided into benzenoid and non-benzenoid compounds. Acyclic or open chain compounds. Acyclic compounds are the open chain structures and they are also called as aliphatic compounds. Alicyclic or closed chain or ring compounds. Alicyclic are the organic compounds in which 3 or more carbon atoms are linked together in a ring. Aromatic compounds. Aromatic compounds are the organic compounds which contain benzene ring and other ring compounds. Benzenoid aromatic compounds are benzene, naphthalene, toluene, indene, biphenyl, anthracene, phenanthracene, etc. Non-benzenoid aromatic compounds are tropylene, etc. Heterocyclic aromatic compounds. A heterocyclic compound is an organic compound in which one or more of the carbon atoms have been replaced by an atom other than carbon. Typical heteroatoms are nitrogen, oxygen and sulfur. Functional group. It is a specific group of atoms in a molecule responsible for the chemical reactions of that molecule. Homologous series. A homologous series may be defined as a series of structurally similar compounds, each member of which differs from preceding or succeeding member by one group, CH2. The members of the series are known as homologs. Nomenclature of organic compounds. Nomenclature is the system of naming of organic compounds. In the early stages of organic chemistry, the organic compounds were named from the source from which they were prepared. For example, the name acetic acid was derived from vinegar because the Latin word for vinegar is acetum. Methyl alcohol was named wood spirit as it was obtained from the destructive distillation of wood. These names of organic compounds are called common names or trivial names. The IUPAC system of nomenclature. IUPAC stands for International Union of Pure and Applied Chemistry. By using this system, we can give a systematic name to an organic compound. The systematic name of organic compound can be derived by identifying parent chain, functional group and branch chain. We also add prefixes and suffixes through which the parent name is used to get the actual name. IUPAC nomenclature of alkanes. Straight chain hydrocarbons. The names of these compounds are based on their parent chain structure and their name ends with a suffix ane. Branched chain hydrocarbons. In this, small carbon chains are attached to carbon atoms of parent chain. These small carbon chains are called alkyl groups. To name branched chain hydrocarbon, the names of alkyl group attached to carbon atoms of parent chain prefix to the name of parent alkane. An alkyl group is formed from saturated hydrocarbon by removing one hydrogen atom from carbon. To name alkyl group, we substitute YL. Some abbreviations are used for alkyl group, such as Me for methyl, Et for ethyl. Alkyl can also have branched chain structures such as isopropyl, tet-butyl. Nomenclature of branched chain alkanes. The rules for naming are given below. First, we identify the longest chain of the carbon in the molecule. The carbon atoms in the parent chain are numbered. It helps to locate the carbon atoms with attached alkyl group. The numbering in the parent chain is done in such a way that the branched carbon atom get the lowest possible numbers. That means the numbering in the given carbon chain is from left to right. After that, the names of the alkyl are prefixed to the names of the parent alkane. Thus, the name of the given organic compound is 3-ethyl 1-methyl heptane. Nomenclature of branched chain alkanes. If the substituent groups are similar, then the numbers are separated by comma and prefixes are used such as given below. If the two substituents are at the same position from both the ends, then the lower number is given to the carbon which comes first in the alphabetical listing. For example, 2-ethyl 5-methyl hexane. Some IUPAC common names are: common name is isopropyl, its IUPAC name is 1-methyl ethyl, and its structure is this. Common name is sec-butyl, its IUPAC name is 1-methyl propyl, and its structure is this. Common name is isobutyl, its IUPAC name is 2-methyl propyl, and its structure is this. Common name is tert-butyl, its IUPAC name is 1,1-dimethyl ethyl, and its structure is this. Common name is neopentyl, its IUPAC name is 2,2-dimethyl propyl, and its structure is this. Nomenclature of branched chain alkanes. To name the multi-substituted compound, the following rules must also be remembered. If there are two chains of equal number of carbons, then the chain which contains more number of side chains is selected. The numbering is done from the end which is nearest to the substituent. For example, the IUPAC name of the given compound is 4,2,2-dimethyl propyl octane. Cyclic compounds. The single-bonded monocyclic compounds are named by prefixing cyclo-straight chain alkane. For example, cyclobutane, cyclopentane, cyclohexane. Nomenclature of organic compounds having functional group S. Functional group defines the chemical reactive nature of organic molecule. In polyfunctional compounds, one functional group is chosen as principal functional group and the remaining are treated as substituents with appropriate prefixes. Some functional groups are given below in the table. Decreasing order of priority for some functional group is carboxylic acids, acid anhydrides, esters, acid chlorides, amides, nitriles, aldehydes, nitriles, aldehydes, ketones, alcohols, amines, alkenes, alkynes, halo, nitro, alkoxy, alkyl. For example, let us write the IUPAC name of the following organic compound. Here, the word root is BUT, but, and primary suffix is ANE, ane. There are two functional groups, ketone and alcohol. Ketone gets preference over alcohol group. Thus, the secondary suffix is 1. The prefixes are methyl and hydroxyl. Thus, the name is 3-hydroxy, 3-methyl-butane, 2,1. Nomenclature of substituted benzene compounds. To name the substituted benzene compounds, these compounds are named by attaching the name of the substituent as a prefix to the benzene. For example, bromobenzene, tert-butylbenzene, nitrobenzene. If more than one substituent is attached to the benzene ring, then the naming is done by numbering the carbon atoms of the benzene ring in such a way that substituents get the lowest possible numbers. For example, 1,2-dinitrobenzene, 1,3-dinitrobenzene, 1,4-dinitrobenzene. In trivial system, ortho O, meta M and para P terms are used as prefixes to represent the relative positions 1, 2, 1, 3 and 1, 4 respectively. For example, ortho-dinitrobenzene, meta-dinitrobenzene, para-dinitrobenzene. Nomenclature of substituted benzene compounds. For more than di-substituted benzene ring, ortho, meta and para cannot be used as prefixes, and the compounds are named by locating the substituents on the benzene ring on the lowest possible number. One substituent of the compound is given number 1, and then the direction of numbering is chosen in such a way that the next substituent gets the lower number. The names of the substituents appear in alphabetical order. For example, we assign number 1 to fluorine so that nitro gets 2 and ethyl gets 4. This compound can be named in alphabetical order as 4-ethyl, 1-fluoro-2-nitrobenzene. When benzene ring is linked to an alkane with functional group, then the benzene ring is treated as substituent. The term phenyl is used to indicate C6H5. Did you know? Messenger spacecraft of NASA has uncovered evidence that not only does water ice exist on the surface of the planet Mercury, but in many places, this ice appears to be covered in a 10 centimeters thick layer of soot-like organic material. Summary. Let us summarize what we have learnt. Organic chemistry is the study of hydrocarbons and other compounds regarded as derivatives of hydrocarbons. Carbon is a tetravalent compound. Pi bond is formed by the overlapping of p orbitals on adjacent atoms. Organic compounds can be represented by complete, condensed and bond-line structural formulas. In 3D representation, the solid wedge represents a bond projecting from the paper towards the observer, and the dashed wedge represents a bond away from observer. Acyclic compounds are the open chain structures, whereas alicyclic are the organic compounds which are linked together in a ring. Functional group is a specific group of atoms in a molecule responsible for the chemical reactions of that molecule. Nomenclature is the system of naming of organic compounds. In trivial system, ortho, meta and para terms are used as prefixes to represent the relative positions 1, 2, 1, 3 and 1, 4 of a benzene ring respectively.
Introduction. Hey kids, today we will learn water, hydrogen peroxide and heavy water. Water is a chemical substance and its chemical formula is H2O. It is a colorless and transparent liquid. It contains one oxygen atom and two hydrogen atoms. Hydrogen peroxide is a combination of hydrogen and oxygen. Its chemical formula is H2O2. Heavy water is a deuterium oxide. It is another form of water which contains hydrogen deuterium isotope. So, throughout this module we will learn water, hydrogen peroxide and heavy. Objectives. At the end of this lesson, you will be able to discuss physical and chemical properties of water, discuss structure of ice and water, distinguish hard and soft water, explain the methods of preparation of hydrogen peroxide and discuss its physical and chemical properties, define heavy water and discuss dihydrogen as a fuel. Water. Water is most common, abundant and easily obtainable of all chemical compounds. It is a crucial compound for man's survival. It can exist in solid, liquid or gaseous forms. It is the universal solvent. 70% of our body contains water. 75% of Earth consists of water. Physical properties of water. It is colorless, odorless and tasteless liquid. The blue or bluish-green tint of water is due to its depth. Water's freezing point is 0 degrees Celsius and its boiling point is 100 degrees Celsius. When frozen, it expands by 1/9 of its original volume. The boiling point of water depends upon the pressure on its surface. The higher the pressure, the higher the boiling point. Structure of water. A water molecule consists of 2 hydrogen atoms and 1 oxygen atom. It has high polarity. The 3 atoms make an angle. The HOH angle is approximately 104.5 degrees. The center of each hydrogen atom is approximately 95.7 picometer from the center of the oxygen atom. As oxygen is more electronegative than hydrogen, the hydrogen atoms end up with a partial positive charge and the oxygen atom with a partial negative charge. This separation of charge produces a net dipole moment on the molecule. The solid form of water is ice and the density of ice is less than that of water. Structure of ice. Ice has 3-dimensional network in which each oxygen atom is surrounded tetrahedrally by 4 other oxygen atoms at a distance of 276 picometer. 3-dimensional structure of ice has got an open space, that is why it has less density and floats over water. Chemical properties of water. Amphoteric nature. The ability of some chemicals act either as an acid or a base is called amphoterism. If a base like NH3 is present, water can act as an acid and react by donating a proton to that base. If an acid like H2S is present, water can act as base and react by accepting a proton from that acid. The self-ionization of water is another example of water being able to react either as an acid or a base. Redox reactions involving water. Dihydrogen can be produced by the reduction of water as given. Chemical properties of water. Hydrolysis reaction. The reaction of compounds with water to form new compounds is called hydrolysis. For example, dinitrogen pentoxide reacts with water to form nitric acid. Hydrates formation. Water form hydrates with metal salts. There are 3 main types. Coordinated complex compounds. For example, nickel 2 nitrate hexahydrate. Coordinate bond is formed between O of H2O with metal ion. H bonded. For example, copper sulfate pentahydrate. Interstitial hydrates. Water is present in some compound as interstitial water. For example, BaCl. Hard and soft water. Hard water. The water which contains dissolved salts of Ca2+, Mg2+, and Fe2+ is called hard water. It does not form enough lather with soap. Soft water. It does not contain dissolved salt of calcium, magnesium, iron. It forms enough lather with soap. It is free from bicarbonates, sulfates, chlorides of Ca2+ and Mg2+. Fatty acids. Those acids which contain higher alkyl chain are called fatty acids. For example, C15H31COOH, C17H35COOH. Hard water forms precipitate on reacting with soap. Reaction of hard water with soap. Hard and soft water. Water hardness is of two types. Temporary hardness. It is caused by the presence of bicarbonate of calcium and magnesium that are, and it can be removed by boiling. Soluble bicarbonates change to carbonates which are insoluble and get precipitated. Clark's method. When calculated quantity of lime is put in, it causes precipitation of calcium carbonate. Permanent hardness. It is the hardness caused by the presence of chlorides and sulfates of Ca2+, Mg2+, and Fe2+. It can be removed by treatment with washing soda or sodium carbonate. Sodium carbonates converts calcium and magnesium salts to insoluble carbonates which can be filtered off. Calgon's method. It is sodium hexametaphosphate. The complex anion keeps the Mg2+ and Ca2+ ions in solution. Ion exchange method. Zeolite or hydrated sodium aluminium silicate is called permuted. NaAlSiO4 3H2O is used to remove Ca2+ and Mg2+. The zeolite can be regenerated by treatment with NaCl solution. Synthetic resins method. Synthetic resins method. Hard water can be softened by using synthetic cation exchangers. They are more efficient than zeolite and permuted. These cation exchangers are large organic molecules containing sulfonic acid, RSO3H group. The ion exchange resin is first changed to the sodium form by treatment with NaCl solution and then used for softening of water. The resin can be regenerated for further use by treatment with NaCl solution. Hydrogen peroxide, H2O2. Preparation. Hydrogen peroxide can be prepared by the action of sulfuric acid or phosphoric acid on hydrated barium peroxide. Anhydrous barium peroxide does not react readily with sulfuric acid because a coating of insoluble barium sulfate is formed on its surface which stops further action of the acid. Therefore, hydrated barium peroxide BaO2,8H2O must be used. Industrially, it is prepared by the auto-oxidization of 2-alkylyl anthraquinols. When 2-ethyl anthraquinol is oxidized in the presence of hydrogen or palladium, it gives hydrogen peroxide. Physical properties. Hydrogen peroxide is a clear and colorless liquid. It has a slightly pungent odor. Hydrogen peroxide is a versatile and environmentally friendly chemical with a wide variety of applications. Structure. Hydrogen peroxide has a non-planar structure. In gas phase, dihedral angle is 111.5 degree. In solid phase at 110 Kelvin, dihedral angle is 90.2 degree. Chemical properties. Hydrogen peroxide can act as oxidizing as well as reducing agent. Oxidizing action in acidic medium. Reducing action in acidic medium. Oxidizing action in basic medium. Reducing action in basic medium. Storage. Hydrogen peroxide should be stored in roofed, fireproof rooms where it can be kept cool and protected from direct sunlight. It is very important that hydrogen peroxide should be protected against all types of contamination. With proper storage in the original containers or in tank installations, the solutions can be stored for long periods without noticeable losses in active oxygen. Uses. It is used as an antiseptic and for mouthwash. It is used in chemicals manufacturing food, water and wastewater treatment. It is also used in biological sewage treatment in cases where there is a lack of oxygen due to overload of biological treatment plants. It is used in oxidation of formaldehydes, phenols, organic chlorine compounds, etc. Heavy water, D2O. Heavy water is the oxide of heavy hydrogen and is also called deuterium oxide. The credit of discovery of heavy water goes to Urey, who first proved that 6,000 parts of ordinary water contains about 1 part of heavy water. Demonstration of heavy water. Firstly, take 2 beakers filled with water. Drop an ice cube which is blue in color in the first beaker and see that ice floats on water. In another beaker, drop another ice cube which is red in color of heavy water D2O. You will see that the ice cube sinks in the water. This is due to the fact that deuterium is heavier isotope than hydrogen and it changes physical and chemical properties of water. Dihydrogen as a fuel. Hydrogen can be used as a source of energy. It involves the production of large quantities of hydrogen electrically and its storage in liquid form in vacuum-insulated cryogenic tanks and used in space programs. Hydrogen can be a future source of energy. Advantage of hydrogen as an automobile fuel. It produces greater energy per unit mass of fuel due to high calorific value. It is pollution-free. Combustion products of hydrogen in presence of air will be H2O and traces of oxides of nitrogen. Internal combustion engines can be easily modified for use of hydrogen as a fuel. 5-point fuel cells generation of electric power with efficiency 70 to 85% have successfully operated commercially in space vehicles. Did you know? Hydrogen peroxide can be used to induce vomiting when a dog has ingested poison. Gold nanoparticles can be used to produce hydrogen fuel.
Summary.
Let us summarize what we have learned. Water is most common, abundant, and easily obtainable of all chemical compounds. The HOH angle is approximately 104.5 degrees. The center of each hydrogen atom is approximately 95.7 picometer from the center of the oxygen atom. Water has the ability to act either as an acid or a base is called amphoterism. The water which contains dissolved salts of Ca2+, Mg2+, and Fe2+ is called hard water. The water which does not contain dissolved salts of calcium, magnesium, iron, etc. is called soft water. It forms enough lather with soap. It is free from bicarbonates, sulfates, chlorides of Ca2+ and Mg2+. Temporary hardness can be removed by boiling and Clark's method. Permanent hardness can be removed by treatment with washing soda, Calgon's method, ion exchange method, and synthetic resins method. Hydrogen peroxide can be prepared by the action of sulfuric acid or phosphoric acid on hydrated barium peroxide. Hydrogen peroxide has a non-planar structure. Heavy water is the oxide of heavy hydrogen and is also called deuterium oxide. Introduction. Today's morning is very good. Yes, Dad. It is a sunny day. So, how is your study going? The study is going very good, Dad. Excellent, Aryan. Dad, I want to ask you something. Yes, dear. Dad, all these vehicles such as cars, trucks, etc. run on fuel. Yes. Does the space shuttle also run on the same fuel? My son, a special type of fuel is used in space shuttle. What kind of special fuel, Dad? They use hydrogen in the external tank to lift off the space shuttle. Would you like to learn more of it? Yes, Dad. In this lesson, you will learn hydrogen and its compound. Objectives. At the end of this lesson, you will be able to locate the hydrogen in the periodic table and define the isotopes of hydrogen. Explain the preparation of dihydrogen, physical and chemical properties of dihydrogen. Explain hydrides. Position of hydrogen in the periodic table. Hydrogen is the first element of the periodic table with atomic number 1. As it has only one electron, so its electronic configuration is 1s1. Because of the dual behavior of hydrogen, it is quite difficult to find a proper place in periodic table as it has resemblance with alkali metals and with the halogens. Like alkali metals, it has only one electron in its valence shell. Like halogens, hydrogen is short only by one electron to complete the inert gas configuration. Dihydrogen, H2. Occurrence. Dihydrogen is the most spontaneous element in the universe. It has about 70% of the universe's total mass. Jupiter and Saturn mostly consist of hydrogen. Half of the mass of the Sun and some other stars made up of hydrogen. In the combined form, it forms 15.4% of the Earth's crust and oceans. Earth does not have enough gravitational pull to retain the light hydrogen molecule, so it is not found in our atmosphere. Isotopes of hydrogen. Hydrogen has 3 isotopes. Protium. Its atomic number is 1 and mass number is also 1. It has 1 proton but no neutron in its nucleus and 1 electron in its 1s orbital. It is represented by symbol H. Its abundance is 99.985%. Deuterium. Its atomic number is 1 and mass number is 2. It has 1 proton and 1 neutron in its nucleus and 1 electron in its 1s orbital. It is represented by symbol D. Its abundance is 0.0156%. Tritium. Its nucleus has 1 proton and 2 neutrons and there is 1 electron in its 1s orbital. It is an extremely rare isotope. Out of 10 to the power 18 molecules of ordinary hydrogen, there is just 1 molecule of tritium. This isotope of hydrogen is radioactive in nature and emits low-energy beta particles. Its abundance is 10 raised to the power minus 15%. Preparation of dihydrogen, H2. Laboratory preparation of dihydrogen. In the laboratory, hydrogen is generally prepared by the action of dilute mineral acids on metals such as granulated zinc. Few pieces of granulated zinc are placed in valve bottle which is fitted with a thistle funnel and a delivery tube. Dilute sulfuric acid is poured through thistle funnel. The acid reacts with zinc, evolving hydrogen, which is collected in jar by downward displacement of water. Pure zinc is not used as it is non-porous and therefore, after some time, the reaction slows down. Hence, granulated zinc is used that is impure and it increases the rate of reaction. Commercial production of dihydrogen. Electrolysis of water. It involves the electrolysis of acidified or alkaline water. We use dilute H2SO4 to make water acidified. Dilute sulfuric acid is enough to make water act as an electrolyte. When anode and cathode are connected to a battery, it produces a small amount of current of the order of few milliamperes and bubbles start appearing in the 2 arms of the voltmeter. The anode collects oxygen and the cathode arm collects hydrogen gas. The reactions taking place are dissociation of H2SO4. H2SO4 gives 2H plus SO4 2 minus. Dissociation of H2O. H2O gives H plus OH minus. Reaction at cathode. H plus electron gives H. H plus H gives H2. Reaction at anode. OH minus gives OH plus electron. 4OH gives H2O plus O2. Overall reaction. 2H2O gives 2H2 plus O2. At the anode, OH minus ions are released in preference to SO4 2 minus ions. This is because it is easier for an OH minus ion to give up an electron quickly than for the SO4 2 minus ion to do so. Since the sulfuric acid itself does not participate in the chemical reaction that is taking place, it can be called as a catalyst of the reaction. Commercial production of dihydrogen. Dihydrogen can be prepared by the action of steam with red-hot coke as given below. The water gas formed is also called synthesis gas or syngas. Then water gas is mixed with steam and is passed over heated Fe2O3 and Cr2O3 at 770 Kelvin. Then CO is oxidized to CO2. Gaseous mixture of CO2 and H2 is then bubbled into cold water under pressure, when CO2 dissolves, leaving behind dihydrogen gas which escapes out. This reaction is called water-gas shift reaction. Properties of dihydrogen. Physical properties. It is colorless, odorless, tasteless gas. It is lighter than air and collected by downward displacement of water because it is insoluble in water. It is highly combustible. It is the lightest of all elements. Chemical properties of dihydrogen. Reaction with halogens. The reactivity of halogens with hydrogen is fluorine greater than chlorine, greater than bromine, greater than iodine. Hydrogen reacts with halogens to give hydrogen halides. Reaction with dioxygen. Hydrogen reacts with dioxygen to give water. Chemical properties of dihydrogen. Reaction with dinitrogen. Hydrogen reacts with dinitrogen to give ammonia. Reaction with metals. Hydrogen reacts with metals to form hydrides, where M is an alkali metal. For example, 2Na plus H2 on temperature 525 Kelvin gives 2NaH. Chemical properties of dihydrogen. Reaction with metal ions and metal oxides. Hydrogen reacts with metal ions and metal oxides to give corresponding metal. For example, reactions with organic compounds. When hydrogen is passed through edible vegetable oils at about 473 Kelvin in presence of finely divided nickel as a catalyst, they undergo hardening and change into edible fat. Uses of dihydrogen. It is used in synthesis of ammonia. Nitrogen and hydrogen passed to heater, where these are heated up to a certain temperature. After that, they are compressed and then passed to heater, where the reaction takes place. After that, the mixture is passed to waste heat boiler, from which ammonia is cooled and then stored, and nitrogen and hydrogen are recycled. It is used in the manufacture of vanaspati ghee. It is used as a rocket fuel in space research. It is used in fuel cells for generating electrical energy. Hydrides. Hydrides are referred to binary compounds that hydrogen forms with other elements of the periodic table except noble gases. Hydrides can be categorized as ionic or saline hydrides. The ionic hydride form between hydrogen and the most active metals, especially with the alkali and alkaline earth metals of group 1 and 2 elements. In this group, the hydrogen acts as the hydride ion. They bond with more electropositive metal atoms. Electrolysis of solution of saline hydride in molten alkali halide produces H2 at anode. The reaction is given as alkali metal hydrides are also used for the removal of last traces of water from organic compounds. Covalent or molecular hydrides. Hydrogen form molecular compounds with p-block elements. Common examples of such hydrides are CH4, NH3, H2O, HF, etc. The stability of these hydrides decreases down the group. For example, in a period, the stability increases with increasing electronegativity. For example, covalent or molecular hydrides. Molecular hydrides are classified as electron-rich molecular hydride. These hydrides have one or more lone pairs of electrons around the central more electronegative element. For example, water has 2 lone pairs. Electron-precise molecular hydride. These hydrides have required number of electrons for Lewis structure. A common example of electron-precise molecular hydride is methane, electron-deficient molecular hydride. These hydrides have lesser number of electrons than that required for Lewis structure. A common example of such molecular hydride is diborate. Metallic or non-stoichiometric or interstitial hydrides. These hydrides are generally formed by the transition metal of group 3, 4, 5 of D- block, Cr metal of group 6, F- block metals. The elements of group 7, 8, 9 of D- block do not form hydrides at all. This inability of metal of group 7, 8, 9 of periodic table to form hydrides is referred to as hydride gap of D- block. In these compounds, H atoms occupy interstitial positions in the metal lattices. For example, SCH2, LaH2.87. Did you know? Boeing unveils new hydrogen-powered aircraft. Boeing has been working to make new aircraft more environmentally friendly. Boeing and others have been developing new aircraft that make use of alternative energy. Further tests with the aircraft will help Boeing understand the best use for the fuel cell and the other technologies it has chosen for the plane.
Summary.
Let us summarize what we have learned. Hydrogen is the first element of the periodic table with atomic number 1. 3 isotopes of hydrogen are protium, deuterium and tritium. In laboratory, dihydrogen is prepared by the treatment of zinc granules with dilute sulfuric acid. Hydrogen is colorless, odorless, tasteless gas and highly combustible gas. Hydrogen reacts with halogens to give hydrogen halides. Hydrogen reacts with dioxygen to give water. Hydrogen reacts with dinitrogen to give ammonia. Hydrogen reacts with metals to form hydrides. Hydrogen reacts with metal ions and metal oxides to give corresponding metal. Hydrides can be categorized as ionic, covalent and metallic hydrides. Introduction. Students, look at this structure. Does anyone know what is this? Sir, this is a benzene ring. Correct, a benzene ring. And now, who will define aromatic hydrocarbons? Sir, aromatic hydrocarbons are those which contain one or more benzene rings. Very good, Rahul. Today we will learn about aromatic hydrocarbons. Come, let's start. Objectives. At the end of this lesson, you will be able to explain aromatic hydrocarbons, recognize and write structures of isomers of aromatic hydrocarbons, comprehend the structure of benzene, explain aromaticity, understand mechanism of electrophilic substitution reactions of benzene, predict the directive influence of substituents in monosubstituted benzene ring, learn about carcinogenicity and toxicity. Aromatic hydrocarbons. Aromatic compounds are a class of hydrocarbons that possess much greater stability than their conjugated unsaturated system suggests. The simplest example of this class of compounds, benzene, was isolated from illuminating gas by Michael Faraday in 1825. In the years to follow, this compound and homologues were isolated by the distillation of resin gums from balsam trees. Because many of the resin gums had fragrant aromas, these compounds were often called aromatic compounds or aromatic hydrocarbons and are also known as arenes. In 1845, August von Hofmann isolated benzene from coal tar. This isolation method remained the chief source of benzene until 1950s. Today, most benzene is produced from petroleum. Simple aromatic hydrocarbons come from two main sources, coal and petroleum. Coal is a complex mixture of a large number of compounds, most of which are long-chain compounds. If coal is heated to about 1000 degrees Celsius in the absence of air or oxygen, volatile components, the so-called tar oil, are stripped out. By fractional distillation, benzene, toluene, xylene and naphthalene as well as many other aromatic compounds are obtained. Isomerism. In benzene, all 6 hydrogen atoms are equivalent, so it forms one and only one type of mono-substituted product. When 2 hydrogen atoms in benzene are replaced by 2 similar or different monovalent atoms or groups, then 3 different position isomers are possible. First one is 1, 2 or 1, 6, known as the ortho. Second one is 1, 3 or 1, 5 as meta. And the third one is 1, 4, known as para, disubstituted compounds. Nomenclature. Naming aromatic compounds isn't quite so straightforward as naming chain compounds. Often more than one name is acceptable, and it's not uncommon to find the old names still in use as well. The benzene ring. All aromatic compounds are based on benzene, C6H6, which has a ring of 6 carbon atoms and has this symbol. Each corner of the hexagon has a carbon atom with a hydrogen attached. A. The benzene ring is named as a phenyl group when it is a substituent. B. Multiple substituents on a benzene ring are numbered to give these substituents the lowest possible numbers. When only 2 substituents are attached to a benzene ring, they can be named by the common nomenclature using ortho, O-, 1 to 2 placement, meta, M-, 1 to 3 placement, or para, P-, 1 to 4 placement. Given compound is 1-ethyl, 2-methylbenzene, O-methylethyl-benzene. Can you name the given compound? It is 1-ethanyl, 3-methylbenzene, M-methylethanylbenzene. Nomenclature of alkenes 2. C. Some common names involving benzene rings that you should know are toluene and orthoxylene. Biphenyl. Notice the numbering convention for this compound. D. Polycyclic aromatic hydrocarbons that you should know are naphthalene. A common nomenclature if only one substituent is on the naphthalene ring system involves the use of alpha and beta. E. The annulenes are large aromatic rings that have 4N plus 2p electrons in a cyclic conjugated system. That is, N is equal to any whole number including 0. The compound 1, 3, 5, 7 cyclooctatetraene is not an annuline. It has 8 p electrons which would yield 1.5 for N. Structure of 10-annuline. Structure of benzene. A chemist, Kekule, in 1865 suggested the following structure for benzene. According to Kekule, 6 carbon atoms in benzene are on the 6 corners of a regular hexagon. Each C atom is attached with one H atom. There are 3 alternate double bonds between 2 C atoms to complete 4th vacancy of carbon. There was an objection to the above-mentioned structure of benzene that it must give 2 orthoisomers, di-substitution, but in actual practice only 1 orthoisomer is obtained. To answer this question, Kekulé extended his theory and argued that the position of double bond in benzene is not fixed, but the double bond system is revolving over the hexagonal ring. He proposed the given structures and said that all C-C positions have a partial double bond character. In the extension of his theory, Kekulé explained that C atoms in benzene were in a state of vibration, and due to this vibration, each pair of C atoms has a single bond half of the time and a double bond the other half of the time. Kekulé's structure failed to explain why benzene with 3 double bonds does not undergo addition reactions like alkenes or alkynes. Resonance 1. Modern instrumental studies confirm earlier experimental data that all the bonds in benzene are of equal length, approximately 1.40
picometer.
1
Picometer
equals 1 into 10 raised to the power minus 12 meter. This bond length falls exactly halfway between the length of a carbon-carbon single bond, 1.46
picometer,
and a carbon-carbon double bond, 1.34
picometer.
In addition, these studies confirm that all bond angles are equal, 120 degrees, and that the benzene molecule has a planar or flat structure. Modern descriptions of the benzene structure combine resonance theory with molecular orbital theory. Resonance theory postulates that when more than one structure can be drawn from the same molecule, none of the drawn structure is the correct structure. The true structure is a hybrid of all the drawn structures and is more stable than any of them. The greater the number of structures that can be drawn from a molecule, the more stable the hybrid structure will be. The difference between the calculated energy for a drawn structure and the actual energy of a hybrid structure is called the resonance energy. The greater the resonance energy of a compound, the more stable the compound. The 2 Kekulé structures that can be drawn from the benzene molecule are actually 2 resonance structures. The hybrid of these structures would be drawn as this, where the circle represents the movement of the electrons throughout the entire molecule. This delocalization of pi electrons found in pi molecular orbitals, is also found in conjugated diene systems. Like benzene, the conjugated diene systems show increased stability. Because of resonance, the benzene molecule is more stable than its 1,3,5 cyclohexatriene structure suggests. This extra stability, 36 kilocalories per mole, is referred to as its resonance energy. Orbital picture of benzene. Because experimental data shows that the benzene molecule is planar, that all carbon atoms bond to 3 other atoms, and that all bond angles are 120 degrees, the benzene molecule must possess sp2 hybridization. With sp2 hybridization, each carbon atom has an unhybridized atomic p orbital associated with it. The overlap of the sp2 hybrid orbitals would create the sigma bonds that hold the ring together, while the side-to-side overlap of the atomic p orbitals can occur in both directions, leading to complete delocalization in the pi system. This complete delocalization adds great stability to the molecule. Molecular orbital theory predicts that overlapping 6 atomic p orbitals will lead to the generation of 6 pi molecular orbitals. 3 of these pi molecular orbitals will be bonding orbitals, while the other 3 will be anti-bonding orbitals, as shown in the figure. The 3 low-energy orbitals
denoted
pi 1, pi 2 and pi 3 are bonding combinations, and the 3 high-energy orbitals
denoted
pi 4, pi 5 and pi 6 are anti-bonding orbitals. 2 of the bonding orbitals, pi 2 and pi 3, have the same energy, as do the anti-bonding orbitals pi 4 and pi 5. Such orbitals are said to be degenerate. Because the electrons are all located in bonding orbitals, the molecule is very stable. Additional stability occurs because all the bonding orbitals are filled and all the pi electrons have paired spins. Molecules that possess all these characteristics are said to have a closed bond shell of delocalized pi electrons. Molecules such as benzene that possess a closed bond shell of delocalized pi electrons are extremely stable and show great resonance energies. Aromaticity. Aromaticity is a property of conjugated cycloalkenes in which the stabilization of the molecule is strong due to the ability of the electrons in the p orbitals to delocalize and act as a framework to create a planar molecule. The 3 general requirements for a compound to be aromatic are: 1. The compound must be cyclic. 2. Each element within the ring must have a p orbital that is perpendicular to the ring, hence the molecule is planar. 3. The compound must follow Huckel's rule. The ring has to contain 4n plus 2 p orbital electrons. Among the many distinctive features of benzene, its aromaticity is the major contributor to why it is so unreactive. The delocalization of the p orbital carbons on the sp2 hybridized carbons is what gives the aromatic qualities of benzene. Preparation of benzene. By the decarboxylation of sodium benzoate. This method is used in the laboratory to obtain benzene. Sodium benzoate is heated with soda lime, and when it gets decarboxylated, that is, removal of carbon dioxide, benzene is obtained. By heating phenol with zinc. When phenol vapors are passed over heated zinc dust, benzene is formed. By polymerization of ethine, acetylene. When ethine or acetylene is passed through a red-hot copper tube, it polymerizes to benzene. By the hydrolysis of sulfonic acid. Benzene sulfonic acid on hydrolysis with superheated steam gives benzene. Physical properties. Aromatic hydrocarbons are non-polar molecules. They are usually colorless liquids or solids. The naphthalene balls are used in toilets and for preservation of clothes because they have unique smell and the moth-repellent property. Aromatic hydrocarbons burn with sooty flame. They are immiscible with water but are readily miscible with organic solvents. Chemical properties 1. Although aromatic compounds have multiple double bonds, these compounds do not undergo addition reactions. Their lack of reactivity toward addition reactions is due to the great stability of the ring systems that result from complete pi electron delocalization, resonance. Aromatic compounds react by electrophilic aromatic substitution reactions, in which the aromaticity of the ring system is preserved. For example, benzene reacts with bromine to form bromobenzene. The bromination of benzene. All electrophilic aromatic substitution reactions share a common mechanism. This mechanism consists of a series of steps. An electrophile, an electron-seeking reagent, is generated. For the bromination of benzene reaction, the electrophile is the Br plus ion generated by the reaction of the bromine molecule with ferric bromide, a Lewis acid. The electrophile attacks the pi electron system of the benzene ring to form a non-aromatic carbocation. The positive charge on the carbocation that is formed is delocalized throughout the molecule. The aromaticity is restored by the loss of a proton from the atom to which the bromine atom, the electrophile, has bonded. Finally, the proton reacts with the FeBr4- to regenerate the FeBr3 catalyst and form the product HBr. You can summarize this particular electrophilic aromatic substitution mechanism like this. Chemical properties 2. In another example of an electrophilic aromatic substitution reaction, benzene reacts with a mixture of concentrated nitric and sulfuric acids to create nitrobenzene. The reaction of benzene with concentrated sulfuric acid at room temperature produces benzene sulfonic acid. When benzene is treated with an alkyl halide in the presence of anhydrous aluminium chloride, alkyl benene is formed. This reaction is known as Friedel-Crafts alkylation reaction. The reaction of benzene with an acyl halide or acid anhydride in the presence of Lewis acid, AlCl3, yields acyl benzene. This reaction is known as Friedel-Crafts acylation reaction. Directive influence of a functional group in monosubstituted benzene 1. A monosubstituted benzene, when treated with an electrophile, could undergo 3 electrophilic aromatic substitution reactions. Each reaction yields a disubstituted benzene as the organic product, which can be identified using the descriptors ortho, meta, and para. A is equal to any substituent. E plus is equal to electrophile. If the relative yield of the ortho product and that of the para product are higher than that of the meta product, the substituent on the benzene ring in the monosubstituted benzene is called an ortho-para directing group. If the opposite is observed, the substituent is called a meta-directing group. Look at this example. We can see that the methyl group is an ortho-para directing group. Directive influence of a functional group in monosubstituted benzene 2. If electrophilic aromatic substitution of a monosubstituted benzene is faster than that of benzene under identical conditions, the substituent of the monosubstituted benzene is called an activating group. Under identical conditions, reaction 2 is faster than reaction 1. Thus, the methyl group is an activating group. All activating groups are electron-donating groups. Common activating groups are if electrophilic aromatic substitution of a monosubstituted benzene is slower than that of benzene under identical conditions, the substituent in the monosubstituted benzene is called a deactivating group. Under identical conditions, reaction 2 is slower than reaction 1. Thus, the nitro group is a deactivating group. All deactivating groups are electron withdrawing groups. Common deactivating groups are carcinogenicity and toxicity. Benzene and polynuclear hydrocarbons which have two or more benzene rings fused together are toxic and possess carcinogenic or cancer-producing properties. Incomplete combustion of organic materials like tobacco, coal and petroleum leads to the formation of such polynuclear hydrocarbons. Cancer is caused when they enter the human body and undergo biochemical reactions and damage the DNA. Some of the carcinogenic hydrocarbons are Did you know? Benzene was first discovered by Michael Faraday in 1825, who called it bicarbonate of hydrogen. In 1833, it was discovered again by Eilhard Mitzelrich, who distilled it from gum benzoin. That's how it gets its name. Since it dissolves many organic and greasy substances, benzene found widespread use in removing paint and organic stains from metal surfaces. In 1849, Charles Mansfield perfected a method for extracting benzene from coal tar on industrial scales. Summary. Let us summarize what we have learned. Aromatic hydrocarbons, despite having unsaturation, undergo mainly electrophilic substitution reactions. These undergo addition reactions only under special conditions. Benzene and benzenoid compounds show aromatic character. Aromaticity, the property of being aromatic, is possessed by compounds having specific electronic structure characterized by Huckel's rule, 4n plus 2 pi electron rule. The nature of groups or substituents attached to benzene ring is responsible for activation or deactivation of the benzene ring towards further electrophilic substitution and also for orientation of the incoming group. Some of the polynuclear hydrocarbons having fused benzene ring system have carcinogenic property.